Alok, I can't hear you.
Can you hear me now?
Yes.
Okay. I was
Morning.
muting until good morning. Or good evening, whichever. I was muting until the time of the talk, till it begins.
Today is not only Professor Mitra's birthday, but also Bengali New Year. Today is Shubha
Ah,
Navabarsh.
happy New Year.
Happy New Year. Wala Boshak. Now I can hear you.
Great.
Professor Ghatak, I had nothing too meaningful to say. I was just talking to Shiva, who's sitting next to me, one of the tech support students. So that's why you couldn't hear me. So
Happy New Year, yes. True.
Happy New Year.
Happy
Shubha
New
Navabarsh.
Year.
Shubha
Shubha
Navabarsh.
Navabarsho. Professor
Gagi.
Khatak, so nice to see you.
Yeah.
Professor Barry, so nice to see you all. I think
Nice to
Professor
see you
Brodsky
also.
has joined, Usha has joined, Professor Haridas is there, Professor Uncle Pramod is there, Nivedita D is there. So lovely to see you all.
sorry, I apologize to interrupt you, Didi. Professor Brodsky, can you hear me?
Yes, I can. I just joined on. Yes.
Excellent.
Good to see all you. Good to
Excellent.
see you, James. Right.
Great. So
Hello.
what I was wondering was, we're about a minute from starting, but because it's going to be, you are going to be next, would you like to quickly test a screen share?
I would like to, yeah. Let me just see if I can do that. Yeah. Does that work at all? Can you see my
So
slide?
I should stop sharing then probably.
No, I mean, if you
Correct.
start sharing, it'll give you an option. Well, would you like to unshare the previous one and share yours? And you say yes. Otherwise, yeah. What do you say?
Hmm. Well, yeah, I'm lost here. Hmm. Hmm. I don't know if I'm doing this right. Let's see. Did you see my slides at all here? No.
Not getting any feedback.
Now, well, I got a cheap fix for this. You could email me your presentation and we can handle the slides from here. I mean, that's always there.
Okay. I'm going to keep trying to share my Keynote file.
Well, once I start sharing mine, I don't know if you'll be able to succeed.
Yes, I see. Yeah, sorry about that. I know I was going to have trouble. Can you see my slides at all here?
No.
Not yet.
Yeah, I have no idea what to do here.
In Zoom, there should be a bar along the bottom of your window with a green
Yes.
rectangle share. If you click on that, it should give you the option to share the particular window with your keynote slide in it.
Okay, thank you. There's a share button.
Yep. If you click it,
Um,
it should open up a window with your window options of which window you want to share.
This is more complicated than I remember.
So Professor Brodsky, can I suggest the following? Since we are now due to
Yes.
start, we can start with Professor
Yeah.
Barry's talk. And meanwhile, you could
I'll
email.
send my, I can,
Yeah, just
I'll email my slides too.
yeah. So
Okay.
wait for your presentation.
But I'm not going to show, the file is longer than I'm going to show, but I'll send you the file. Okay.
Excellent.
But anyway, I don't know why.
No worries. I mean,
Why?
that's not a problem. It happened with several speakers yesterday. Great. So
Yeah.
I think we're all set to start with day 2. And so welcome, folks. Welcome back. And today is Professor Ashok Nath Mitra's birthday. And as was pointed out by Professor Joy Ghatak, we also have the Bengali New Year today. So in Bengali, though I'm not a Bengali, Shubha Navavarsha, please excuse my rusty Bengali. And with that, I would now request the chairperson of our session 1, day 2, Professor Usha Kulshrestha, to kindly take over. Thank you.
Thank you, Professor Alok. Good morning, everybody, and welcome to the first session of Professor A.N. Mitra Memorial Meeting and Lecture. I am Usha Kulshrestha from Kirodimal College, Delhi University. So in this session, we have 2 talks by 2 distinguished professors. So each speaker will have altogether 30 minutes. So without further delay, let me invite our first speaker, Professor James Berry from Iowa State University, Ames. And he is going to speak on ab initio approach to hadrons and nuclei. So please, Professor James.
Thank you very much, Professor Kulshrestha, and also thank you to the organizers for this honor to speak at the A.N. Mitra Memorial Conference. I had the great pleasure to meet Professor Mitra during a visit to Delhi some years ago and to discuss some of his pioneering work in analytical treatment of hadrons, which was motivating work from my earlier works on in the area that I'll be talking about today. So the basic idea that underlies what we're talking about is that we have a theory called the Standard Model, which we believe contains predictive power for all the fundamental processes that brought the universe to the present time, all the fundamental reactions of hadrons and nuclei, and would be also fundamental to predicting processes, for example, for energy generation in the future. So this is what defines our starting point, or first principles, or ab initio treatment of hadrons and nuclei. If we can succeed in this approach, then we should be able to explain and predict nuclear phenomenon and use any discrepancies that are found between theory and experiment to reveal new physics. That's the ultimate goal here. So just a quick reminder of the background here. The primary story of hadrons and nuclei starts with the QCD Lagrangian and then includes electroweak interactions as well. So there are a number of very well-known approaches that are for non-perturbative treatments, and also you have your standard Feynman covariant perturbation theory. Our particular approach features using Hamiltonian field theory, which actually traces we trace our roots back to the pioneering work of Professor Stan Brodsky and Professor Hans Christian Pauli, and I'm delighted that he'll be also presenting this morning. So basically, the workflow that we talk about is once you start with the Lagrangian, is traced in the standard treatments along the lines that are in this left-hand column here. But I'll be discussing some of those steps in a little more detail, but that's just a quick reminder of the flow of the work that we're talking about. We also trace the roots of what we do back to the pioneering work of Paul Dirac, as summarized in his work in 1949, where he introduced 3 relativistically consistent treatments of Hamiltonian dynamics. We are most familiar from the textbook physics standpoint of the so-called equal time or instant form, where the starting point is to quantize the system on a fixed time surface, where time is the 4th component or 0th component of a 4 vector. What we do is following what's called Dirac's front form, where the starting point is a surface tangent to the light front. And the Hamiltonian in the system is going to evolve the system in so-called light front time, which is a linear combination of 2 components of the spatial four vector. In this approach, the advantage is that you have, of the 10 total generators of the theory, 7 are kinematic and 3 are dynamic, including the Hamiltonian itself, represented by P minus here. And one of the advertised advantages of this approach is a favorable dispersion relationship that relates the energy to momentum and looks a lot like a non-relativistic kinetic energy relationship, although everything is fully relativistic here. This has some advantages for taking advantage of many of the developments in non-relativistic many-body theory over the past few decades. So we're going to follow that approach. So to summarize what you get from the QCD as well as from the QED Lagrangians, we can draw them in terms of elementary vertices once you picked the light front gauge as your choice. So you have your fermions emitting and absorbing gauge bosons, be they photons or gluons. And you have an instantaneous interaction, so-called instantaneous fermion interaction, and an instantaneous gauge boson interaction coming from the elimination of redundant degrees of freedom. For QCD, you pick up additional vertices, very familiar triple gluon coupling, quartic gluon coupling, and a couple of instantaneous gluon exchanges as well. But in a nutshell, that's it. So the Hamiltonian is completely defined in terms of these vertices as well as the associated kinetic energy terms. So it has a simplicity to it. Of course, everything is in color space and so on. And after that, it comes down to details. How do you actually solve a problem expressed as a Hamiltonian of that form in a non-perturbative scheme? So in the original works of Pauli and Brodsky, they introduced something called discretized light cone quantization, where everything is done in a mesh in momentum space. Together with Stan and other collaborators, in 2010, we introduced basis light front quantization, where fields are expanded in a more general way as linear combinations of destruction and creation operators, where the functions F are rather general and satisfy very simple conditions. And the A's are the usual commutation and anti-commutation, anti-commuting and commuting operators. So the standard conditions that we would invoke for these otherwise arbitrary functions are orthonormality, represented here. And in momentum space, we work with the variables of transverse momentum and light front momentum fraction, or Bjorkane X. So that's the orthonormality condition for these functions. And then there's a completeness relationship as well, where you sum over all possible states of that function space. Now, aside from that, it's very general and arbitrary. Of course, you want to be efficient when you do your computations. So it pays to pick convenient functions. And again, inspired by the work of Professor Mitra, the harmonic oscillator comes to mind as a favored choice. In these coordinates, we would choose a two-dimensional harmonic oscillator function where the quantum numbers are radial quantum number little n and angular momentum projection quantum number m. So those would be the basis functions, which are also familiar to people who work with ADS-QCD. For the longitudinal degrees of freedom, we will pick either the original DLCQ momentum space wave functions, or frequently the Jacobi polynomial basis, a set of Jacobi polynomials multiplied by a convenient factor to manage endpoints. So that all being said, it's good to stand back and ask the question of where do we see the symmetries in the problem? Well, with this set of choices that we've introduced, we can set up our calculations to have a fixed baryon number, a fixed charge, 0 being allowed, 1 for proton space, and so on. Or also, depending on baryon number, you would also be able to do baryon number 0 and mesons with various charges. We also conserve total angular momentum projection, J sub z. So our many parton basis states will have fixed total angular momentum projection, J sub z. And as a result of that, any single calculation we do produces all states of the system with total angular momentum greater than or equal to that angular momentum projection. We insist that our many parton states satisfy the Bjorkian sum rule. Each and every basis state satisfies that. And when we work with DLCQs, there's a longitudinal momentum regulator called K, also called the resolution of the system. When we work with the Jacobi basis, there's another condition to satisfy, which is the sum over the individual light front Jacobi variables for all the partons in a single state has to be less than or equal to a cutoff value. So these serve as regulators. On the transverse two-dimensional harmonic oscillator, in order to manage boost invariance, to retain boost invariance, we would have to have our many parton basis states constructed in such a way that the quanta of the oscillator added over all the partons in a single many parton basis function state falls within a cutoff called N max. And these are the regulators that we would like to remove to reach the continuum limit. The continuum limit is removing all regulators. So we work in the internal coordinates defined in this fashion, such that the total transverse momenta of all partons in every many-body and many-parton state is equal to 0. Then in addition, we actually, if you might have noticed this, the basis function space is actually overcomplete because it's a single parton basis, but we can manage that by introducing a Lagrange multiplier term, which pushes all states of excited center of mass motion higher up in the spectroscopy and away from the physically interesting states. A couple more symmetries to think about. We work within a global color singlet space, so all many parton states are global color singlets. I've already mentioned the choice of gauge, and there's an optional Fox-based truncation to simplify the calculations to make them more manageable. And this attempts to be a fully complete list of the symmetries that govern the calculations that we're talking about. Now, I'd like to quote from Stan Brodsky the fact that light front wave functions, which we can express in the following way, these are the functions that are the amplitudes of our Fox space states. This is your many parton Fox space state in momentum and helicity space for n partons. You're summing over all the n parton states you care about, and you're integrating over all these internal variables to come up with a hadron with total momentum P, total angular momentum J, and total helicity lambda. So these are the objects of interest to solve for. Their overlaps produce quantities of experimental interest, like parton distribution functions, form factors, and so forth. So we can imagine this overall scheme introduced by Stan, where you start with the most general transverse momentum distributions at the top, which are basically products of light front wave functions. Performing various integrals, you collapse these down to other simpler form factors for more direct comparison with experimental measurements. If you integrate and sum out everything, you come up with some total charges of the system. But along the way, you get very popular things like form factors and parton distribution functions. Again, all this emerging from your solutions and eigenvalue problem, as it'll turn out. Okay, so just jumping forward now. So if I want to describe a meson in this kind of framework, I would start with the valence sector of quark, antiquark, and then I would add various sectors, including gluons. I could have a pure glue sector allowed, multi-quark, multi-antiquark, mixtures of quark, antiquark, and gluons, and so on. Similarly, for a baryon, I would start with the valence sector and then add gluons and quark-antiquark pairs on up the line as far as I can go in practical terms. Now, I advertise nuclear physics, so it's useful to also think about deuterium. Deuterium would start with a valence space of 6 valence quarks, and to which you would add, again, quarks and, quark-antiquark pairs, gluons, and so forth, as far up as you can go. Now, that sounds like a nice thing, but there's numerical challenges. The basis spaces that we talk about very quickly achieve dimensions which challenge the largest computers on the planet. So I can look at this a number of ways. If I fix my cutoffs at these values and look at the space and spin degrees of freedom as a function of parton numbers, they increase basically exponentially. So as soon as I get to 7 partons, which are some of the states I've listed up here, so I actually get to 8 here. Here's a 7 parton state. I'm up around dimensions of 10 to the 10th, which would strain even the largest computers on the planet. Another way to look at the calculational challenge is to fix the system, baryon, meson, deuterium, and plot all the Fock sectors that contribute as a function of Nmax, which is set equal to Kmax. And again, an exponential increase appears. This particular plot here characterizes what we call full basis light front quantization, where you keep everything consistent with these regulators. And that's the ideal problem, and that's what we're working towards at the present time. Now, currently, here's an update or status report on where we are. Work in progress, so this is preliminary results. If we take a baryon and include all basis states up through, say, 3 quarks and 3 gluons with various other quark-antiquark pairs included, so you have SU3 flavor for your C quarks, and you have gluon configurations going along with your valence quarks. The total Hamiltonian is actually involving now all vertices that I'd introduced earlier. All vertices of the QCD Hamiltonian and light front gauge will be active in a Hamiltonian written down in this particular Fock space. So that's a very challenging problem. Here's some of the analytical forms. We do have some preliminary results to show. Of course, there are parameters in the theory. There's the masses of the quarks that are involved, and there's the coupling constant. There's a basis space parameter, a couple of basis space parameters characterizing the harmonic oscillator's role in the problem. These parameters are fixed to get the mass of the proton to be the physical mass, and the form factors of the proton to be close to the experimental form factors. Everything else is a prediction. So here's a snapshot of what we find for the proton. The valence sector takes about 46.5% of the state, and then all other sectors are spread around all the other sectors in the picture. But the second largest sector, in fact, the largest sector, is the 3 quarks, 1 gluon, which is almost a natural sector to expect to be competing with the 3 quark sector, because that's where your first entrance of an interacting vertex appears. But then much smaller percentages for the others, notably the 2 gluon sector, well, along with the valence sector, has a 5% probability. And we expect that percentage to grow as we add more gluon sectors, as well as the 3 gluon sector will grow as we add, say, the 4 gluon sector. This is just a natural progression. So what we interpret our results to be at this stage is a representation of the proton at some initial scale where these Fox sectors are appropriate to that scale. And the regulators in the problem are the regulators that define the UV and IR cutoffs. A typical type of result you can get would be your parton distribution functions for the down quark, the up quark, and the gluon, behaving more or less as you might expect when multiplied by X. And then you can get the strange, the anti-up and the anti-down from the C quark distribution. Their PDFs emerge as well. So all these results are emergent from the spectroscopy calculation. Lots of follow-up work will progress from this point, but I want to spend the remaining couple minutes talking more about the corresponding problem in the nuclear physics side of things. So what we view the overall game plan is starting with what I've just been talking about, how you move from quarks and gluons to the baryons and mesons. But then we want to go into nuclear physics as well. To make this jump will be a number of years in the making, but we expect to see emergent from that with appropriate treatment of chiral symmetry, an effective field theory of protons, neutrons, and pions, similar to what Weinberg introduced. So that should be an emergent prediction of this whole treatment. And just to remind you of what the Feynman effective field theory looks like, you have two nucleon forces which are built out of various chiral orders in perturbation theory by exchanging mesons between nucleon lines. And you go all the way up as far as you care to go in diagrammatic chiral effective field theory expansions. Along the way, you predict 3 nucleon forces and eventually 4 nucleon forces. So everything here can be fixed today in today's world by studying two-body scattering data, nucleon-nucleon scattering data, except for certain so-called low-energy constants, which must come by fitting, say, a binding energy of a 3-body system. But once they're fixed, you have a predictive theory of the version of Feynman's chiral effective field theory. And we have been pursuing this in the low-energy ab initio nuclear structure game using the so-called show model, which again is a Hamiltonian eigenvalue problem where the states are expressed in terms of, in this case, Slater determinants of 3-dimensional harmonic oscillators. 3-dimensional because it's a non-relativistic quantum eigenvalue problem. And I'll skip through this just quickly to save time and point out that again, the model spaces grow exponentially as you increase the complexity of the nucleus you're talking about. The dimensions quickly get up to trillion dimensional sizes beyond the scope of current extreme scale computing. They get even larger if you start putting in 3-body forces and 4-body forces, which are coming from chiral effective field theory. Nevertheless, a lot of progress has been made and enough results are obtained that one can extrapolate to the infinite matrix limit. And carrying out those calculations with derived chiral effective field theory Hamiltonians has produced what today would be called these green dots for the binding energies of light nuclei from helium-4 up to carbon-12 with uncertainties coming from 3 sources. The numerical uncertainty is actually the smallest, even after extrapolation. The chiral truncation uncertainty is the largest. That's because we only work here up to next to leading order, including 3 nucleon forces. That's our state-of-the-art up to the present time. And this gives beautiful spectroscopy of light nuclei.
Hello.
Yes, you want me to wrap it up? Very good. Beautiful spectroscopy.
5 minutes.
Yeah, and I want to save some time for questions. So I'm going to fast forward now and just say we have calculations now through next to leading order, but they're not complete chiral interaction. They look very good. If we make some other approximations to the interaction, we can use our many body techniques to, among other things, predict the existence of a tetraneutron, which has recently been confirmed. We can look at exotic systems like the so-called Hoyle state of carbon-12 and see its 3-alpha structure. In a recent Nature Communications paper, we showed that, and so on. But many things lie ahead. Let me just wrap this up by listing overall what I consider some of the most outstanding challenges that, in principle, this kind of approach can offer insights into with predictive power. And so, but again, I remind you of the bottom line, which is the ultimate goal, is to make precision tests of this ab initio theory, tracing its roots all the way back to QCD and QED, with high precision experiments to see if we can detect new physics. So it's been my honor to present here at this Mitra Memorial Conference, a testimony to this true giant in the field of theoretical physics. Thank you for your attention. Welcome your attention. Well, welcome your questions.
So please, session is open for question answer.
Professor Haridas, it seems, has a question.
You're muted, Professor Gargi.
Okay. Well, this is an age-old question that in approaches like light front, manifest Lorentz invariance is lost. And you have to, for example, in string theory, in the light cone quantization, to check that the algebra of Lorentz generators is correct requires a lot of work. So what
Yes.
are similar challenges in your approach?
Okay, so the symmetries are the symmetries of the original framework set up by Dirac, and those are, for the most part, respected explicitly in the choice of the many parton basis that we work with. There is a slight breaking of angular momentum symmetry in the problem, and that is systematically restored by going to larger basis spaces and more complete Fock spaces. So we're not worried about it. It's a small amount of breaking. We can quantify it and see it, and we can also see that it's reduced by going to larger basis spaces. All other symmetries are, the dynamical symmetries are more difficult to test, of course, but the kinematic symmetries are all seem to be available to us and respected, except for the rotational one, which is, as I said, systematically improvable. But
My
that's a
second
good
question
question.
is, your whole approach seems to be rather perturbative in spirit. How do you manage to capture things like confinement in this approach?
Okay, so in everything I showed today, there is no confining interaction. In the earlier years, we were using a phenomenological confining term. So right now, what we're doing is we're relying on the gluon dynamics to give rise to confining behavior. Now, in the limited basis space calculations, everything is confined automatically by the choice of the basis space. So we can't make fundamental tests of whether confinement is emerging without going to successively larger basis spaces and successively larger Fock spaces. And that's part of the future agenda. So we actually cannot say at this moment whether or not confinement is present in our is emerging from our calculations.
Thank you very much.
It's too limited. Yeah, thank you for your questions.
Maybe we can take one more question if there is any question.
Yes.
Yes, Professor Alok.
Sorry, I just had a dumb question. Am I right in my understanding that in this basis light front quantization basis, when you talk about, for example, the beta meson, I saw that it was written as a combination of a QQ bar and a QQ bar G and a GG. So does that mean that you guys make no distinction between a glue ball and a meson?
Correct. That is correct. So in principle, the spectroscopy that we're calculating, which includes a tower of excited states, could be analyzed to see which states are dominated by the pure glue sector, for example. But it would be a fully mixed calculation. Every state would in principle have all Fox sectors involved. But you might be interested in, we would be interested in, as these calculations move forward, in finding out if there are selected states in the spectrum which are heavily dominated by the pure glue sector.
Okay, thank
That's
you.
right. Yeah, so a postscript to that is we've been concentrating on the baryons at the present time, but there's another part of our group that is working up now on the mesons also. So we may have more to say about that in the coming year or so. It's a good question.
So thank you, Professor James. It seems there are no further questions, so we can move on. So it is now we invite our next speaker. So it is my great pleasure to invite our next speaker, Professor Stan Brodsky from Select Theory Division, and he is going to speak on recent advances in light front physics. So please,
Thank you.
Stan.
Yeah, back now. Oh my God. All right. Hmm. Okay, here we go again. Ay. All right. 1 second, I'm having trouble here. Oh. 1 second. Oh my God, what's wrong here? Oh my gosh, okay.
It seems.
Professor Kulshresht, Professor Daya Kulshresht, perhaps you could, we had requested Professor Stan Brodsky if you could email us, maybe he could email you his presentation. We can handle his slides from here. I don't know.
Ali, I could not get your question.
I think it wasn't from two devices, therefore the echo.
Yeah.
It's not me, I don't think. Okay. Okay, there I am now. Let's see, can I show my slides?
Yes, indeed, please. So as Professor Jim Berry had said, do you see, if you hover in the lower part of the Zoom window, you would see a green rectangle with a vertically.
Yeah, I'm doing that.
arrow.
Yeah, I'm doing that green.
Okay, so you click on that, and assuming that you have your presentation file open, you would see it on that window that would have opened. You click on that once, and you click on share.
Oh, doing again. Also, I sent my file. If you have it, I don't know.
I haven't received it actually.
Oh, geez, that's because it's too big, and I've even sent a shorter version.
Oh, okay. Well,
PDF.
Let's see, how do we work around this? Something somewhere around this. He has emailed me the file, but it's too big. It hasn't reached me.
I sent a shortened version. I sent a PDF version as well, because it kept rejecting it because it's so long.
Right. Gmail Drive. Yeah, Google Drive. Professor Brodsky, here's what you could do. You could email me just the shorter of the two. That's
I did already. Yeah, I did again. Let me just try
Just-
one more
okay,
time.
And the other thing is you could perhaps upload it to Google Drive if you have a Gmail
I tried
account.
that. Yeah, and I thought I was doing that too. My God,
And-
I'm really having a lot of trouble. Maybe
Okay.
I should just say, give the talk orally. I don't know. Let me just see here. I'm doing the
So-
share button.
The advantage of uploading it to Google Drive is that you don't have to send the file per se. You just have to share the link.
Yeah,
That we can download it. I mean, if that.
yeah, I'll try one more time if you have more patience here.
Yeah.
Yeah. I don't know why it doesn't work with the share. I've never seen that problem before. Boy.
Oh, I think there'll be an additional complication. You'll have to give the person you're sending the permission to access the file also.
Yeah.
That'll be a two-step process. Yeah. Oh, well. Except contact of somebody. But sharing it on WhatsApp is going to be more not trivial, right? So the huge file. That depends on how big is your PDF?
Oh, about 28 megabytes or gigabytes.
Oh,
Yeah.
that's trivial. So do you have, by any chance, are you in WhatsApp contact with, I don't know, Professor Usha Kulshrestha, Professor Daya Kulshrestha? You could just
send it there too. Yeah.
send them via
Maybe I could
WhatsApp.
I could maybe just give the talk orally. I don't know. How about that?
Oh, well, that's another way to go. Well, we leave it to you.
Yeah, I'll just talk about, actually, James Very just gave a wonderful introduction to what I'm going to talk about. And it does follow on what Professor Mitra, a great scientist, worked on. And that's QCD at the amplitude level, factorization theorems, counting rules, the front form, light front theory, the application of nuclear amplitudes. He was at SLAC in the early days, and he worked on things that I worked on with Ben Chertok. So I got to know him then. And so that's wonderful. So he also worked on the spin dynamics of the three-quark wave function in the light front theory. So he worked on that. It follows on the light front follows on the work of Dirac. We heard James Very talk about this. This is way back to 1949. Dirac had showed, in fact, that if you use the front form, that is light front time, tau equals t plus z over c, then in fact all the answers are causal and boost invariant. So it doesn't depend, none of the observables depend on the frame of the rest frame of the observer. So everything is really Lorentz invariance and causal. So even, in ordinary equal time, you don't even have causality. So the famous formula is the Dirac front form, where in fact the form factor is just the overlap of light front wave functions. The light front wave functions are functions in momentum space of the x variables, that's the k plus over p pluses, the k perps, the transverse momentum, and the spin projections of each hadron. And they add up with the right sum rules, in fact, to the momentum of the hadron. The sum of the x is 1, and the sum of the k perps is the transverse momentum of the hadron, or 0. And the case of the helicities as well. So everything's invariant under boost and independent of the momentum of the hadron as well. So the form factor is just the overlap of two light front wave functions, and we heard about this. If you know the wave function, psi of x and k perps on one side, and you know the other wave function in the final state, then you can compute all the form factors, every one of them. And in fact, it goes on and on. You can actually, Larse and Pasquini showed, in fact, that if you know the light front wave functions, you can evaluate the overlap and get virtually every observable exclusive variable, inclusive variable. You get factorization theorems, you get de Glapp evolution, herbal evolution for exclusive processes, and all the factorization theorems. If Lepage and I use that formula to prove the exclusive process perturbing QCD, we define what's called the distribution amplitude, which is the integral of the transverse momentum of the valence state. That has much of the physics of each hadron. And you get a rigorous QCD analysis of exclusive processes. You get the hadron distributions and what's called the herbal Efremov-Radjushkin-Brodsky-Lepage evolution equations. And if you start with the Lagrangian of QCD, you can systematically derive the Hamiltonian of QCD, but in front form time. And the light front Hamiltonian is the sum of the kinetic energies, which is m squared plus k perp squared over x, plus all the interaction terms. And you can get a complete description of QCD in principle from this by diagonalizing the light front Hamiltonian. And if you diagonalize that light front Hamiltonian, you get all the hadron masses, every one of them. And the eigenvalues are not energies, but the invariant mass squared of each hadron. And then the projection on the free Fock basis is, in fact, the light front wave functions I just described and James described is the description of all the hadrons in terms of their Fock space. And when you use this, you get all the counting rules. You get the core counting rules that they goes a power 1 minus x, just to the twice the number of spectators minus 1 as you go to large X. You get the form factors at large Q squared, that 1 over Q squared to the number of constituents minus 1. You get all the hard exclusive reactions, PP scattering and so on. And just by counting the number of particles, active particles, you get the leading power. And you get the same thing for inclusive processes. You get all the counting rules at large X and so on. Now my own slide it's not moving. All right. Oops. So the one way to deal with this is to actually diagonalize the matrix. And I originally started this with Hornbostel and Pauli, and now we have, in fact, this wonderful work on basis light front quantization by James Very. So what you do is you write down a complete momentum space description of all the Fock states, and in principle, you can diagonalize the light front Hamiltonian and get all the eigenvalues. In practice, you're limited by just the size of the matrices. You actually, the trick is to use actually a simple momentum space representation, which is really discrete. And then you can give this to the computer, and you can diagonalize that light front Hamiltonian. And what you're doing is using periodic or anti-periodic boundary conditions. So then you derive all the counting rules and so on, and you get fantastic results. In the case of James showed lots of different results. In fact, you can get from this, including if you can actually get the complete quark-gonium spectrum. You also derive the counting rules, and for example, PP to PP, the differential cross-section goes like a function of angle over s to the 10th, and that works remarkably well over many angles. And you also get what's called spin exchange, that is, you can exchange, if you do K plus P, you get the right answer by just exchanging an up quark, and you get the interchange amplitude, which gives you the basic angular distribution, 1 over U, 1 over T squared, of the matrix amplitudes. So the challenge for all of us now is to compute hadron structure, spectroscopy, and the dynamics from QCD itself. And you want to have color confinement. We heard about that. You want to understand the origin of the QCD mass scales. You want to understand meson and baryon spectroscopy. You want to understand exotic states like tetraquarks, pentaquarks, gluonium, of course. And then the fact that actually all the slopes of Regge behavior are universal in both N and L. The meson trajectories and the baryon trajectory, Regge trajectories, if you go up to large S at fixed T, all the slopes are the same. How do you explain that? You also get an almost massless pion. If you have a zero mass input quarks, you get a zero mass pion. That's remarkable too. That gives you the Gell-Mann chiral symmetry breaking. And also you want to derive the QCD coupling at all scales, not just at large momentum where you see the asymptotic freedom and so on. You also want to eliminate scale uncertainties and scheme dependence. And you can do this with what's called the BLM or PMC. That's the principal maximum conformality. There's a field of that. So we were looking for a first approximation to QCD, which is comparable in simplicity to Schrödinger theory in atomic physics. It's relativistic, frame independent, color confining. And you want to understand the origin of the hadron mass scale, even if the quark masses are zero. And the new approach that I'm going to talk a little bit about was done with Dash and Dorsey and de Terman, and that is using what's called anti-de Sitter space QCD light front holography. Holography is because we're actually using one additional space-time dimension in an ingenious way. So you start with the exact light front Hamiltonian, which has got the kinetic energy terms. That's the K perp squares plus M squares over X's. And then all the interactions, one gluon and so on, exchange. And you get this wonderful light front Hamiltonian, which is in principle solvable, but very difficult to solve. So instead, one's using, in fact, a trick, which is called light front holography, where in fact you replace, in the case of a two-body, two-particle equation, that could be quark anti-quark, or in the case of baryons, quark diquark, you can actually get a potential, which actually is written as U of zeta. And that unfortunately you don't have it in front of you, but I have it here. And that is you introduce a variable zeta where zeta squared for, say, a pion or a meson is x times 1 minus x, the light front constituents, times b perp squared. That variable is remarkable because zeta squared is actually the key variable to hadron physics once you study it, because it's really what you get as an effective two-particle equation when you reduce all the higher Fock states. The actual key variable is the zeta squared. Again, x1 minus x times b perp squared. And then you get a light front Schrödinger equation, which goes like d by d zeta squared. That's the light front kinetic energy. It's equivalent to k perp squared over x1 minus x. And then there's an angular momentum term, which is 1 minus 4 alpha squared over 4 zeta squared. That's the usual orbital momentum term that you know in non-relativistic physics, but it's now completely covariant and frame independent. And then a potential U of zeta. And the U of zeta turns out from this light front holography to have an amazing simple form. It's kappa to the 4 zeta squared. It's like a harmonic oscillator. So again, zeta is the critical variable, a to x1 minus x b perp squared. And there's an extra term, 2 kappa squared L plus S minus 1, which just comes from kinematics. This equation, which is just a simple two-body equation with the variable zeta squared, is, again, U of zeta, the potential is kappa 4 zeta squared plus the kinetic energy term. That automatically gives the complete two-body spectrum. This is something I showed at Terramon Dash and Lorsay. It's rather remarkable. And what you're doing is you're eliminating the higher Fock states, all the retarded interactions, and so on. You're getting remarkable simplicity with this one potential. If you like, it's a semi-classical first approximation of QCD. So you get this light front Schrödinger equation. Again, it's minus d by d zeta squared. That's for massless quarks. That's k perp squared over x1 minus x. And then 1 minus 4L squared over 4 zeta squared. That's the orbital momentum. And then this amazing potential, which is confining. U of zeta, which is kappa to the 4 zeta squared. And then an extra kinematic term, 2 kappa squared L plus S minus 1. Now, if you, because we're scale invariant, actually the units are not specified. But if you pick in our units, kappa equals 0.5 GeV, it really reproduces the entire hadron spectrum. It's rather remarkable how it works. There's work by D'Alfa, Fubini, and Furlan, and Fubini Bervinci, which is similar. So the first thing you look at is the Regge spectrum. Out of this confining potential, this simple one-body equation, you get the whole meson spectrum, and it's linear in L, it's a Regge spectrum. And then you get the baryons, which are quark diquarks, and they're exactly the same answer. The same slope is exactly the same in terms of kappa half of GeV. So you get exactly m squared linear in 4 kappa squared. And you get the same slope in both n, the principal quantum number, and the orbital momentum. And you get the same result for both mesons and baryons. The only difference is that in the case of the mesons, the spectrum is 4 kappa squared times n plus L meson. That is the orbital momentum in the mesons. And in the case of the baryons, it's 4 kappa squared and n plus LB plus 1, where LB is the orbital momentum between the quark and the diquark. So this is exactly what you see in nature. You see the pion trajectory, the pi B1, pi 2, B3, pi 4, and so on, B5, exactly parallel with the proton, which starts out 940 and then goes up to the 1520, the 1680, and so on. So you get the universality of Regge slopes, both not just in L, but in N as well, exactly the same slope. And if you make this one shift of the orbital momentum of the mesons compared to the baryon by 1 unit, then you see, in fact, that the meson spectrum and the baryon spectrum fall right on top of each other. That is the rho spectrum, the rho omega spectrum, and its Regge recurrences exactly duplicates the delta trajectory. That's rather remarkable. And that's a kind of supersymmetry, because what you're doing is actually relating mesons with baryons, bosons with fermions, and they have exactly the same mass. And this works experimentally to very high accuracy. So there's a hidden supersymmetry in QCD between mesons and baryons. The mesons are quark antiquark, the baryons are quark diquark. And that's rather remarkable how that works. And if you go back to the heavy quarkonium, which is what James Very did with the same potential, harmonic oscillator potential, you reproduce basically the whole heavy quarkonium spectrum. So where does this all come from? It's actually what's called the dilaton modified anti-de Sitter space. And what happens is if you start with the action as e to the phi of z, and then r squared over z squared, and then the normal kinematic dilaton in the fifth dimension, you actually see that, in fact, if you pick e to the phi of z, the prefactor, as e to the plus kappa squared z squared, it gives you exactly what I spoke about before. And in fact, it's really an example of what David Gross called a duality of QCD with string theory. That is, you go to one extra dimension in fifth dimension, and that one extra dimension in z reproduces, in fact, everything I said in zeta in our world. So you take this action in the fifth dimension, and you can map it exactly into our world. Klebanov and Baldacci did something very similar. And what happens is you get then this remarkable result that the fifth dimension has a potential, has a behavior, an action prefactor, which is e to the plus kappa squared z squared. This is what I did with Gita Taraman originally. And when you then realize that the variable z in the fifth dimension is this variable zeta in our world in 3 plus 1, the var zeta is actually, zeta squared is x1 minus xb perp squared, then you reproduce this simple one-dimensional light front equation, which represents the entire meson spectrum, as well as the baryon spectrum, if you realize that the baryons are really quark-diquark structures. And again, it reproduces the entire hadron spectrum with Regge trajectories, universal trajectories in N and L and baryons. And then if you take those solutions, you get the eigenfunctions. The eigenmasses are the m squareds. The eigenfunctions are the light front variables. And you can then calculate then the psi of x and k perp squared exactly from this potential, from this simple one-dimensional light front equation, and then use the Drell-Yan-West formula to compute form factors. And what happens is you can use what's called a Soper formula, in fact, which allows you to integrate one variable out, and you actually get very simple results for form factors, analytic formulas in terms of the K1 Bessel function. So you get this remarkable ingredients. So you get the fact that the wave functions in the fifth dimension angle variable, which we call variable z, is exactly the same wave function in physical space, but in the terms of the variable, the wave functions are all in functions of zeta, where zeta is the square root of x1 minus x b perp squared. And so this gives you the light front wave functions, and you actually understand it for all n, all orbital momentum, internal orbital momentum, and so on. So this is actually a remarkable advance, I think, that in physics. And this is called light front holography. It originates from this anti-de Sitter space model of softwall QCD. And you get this, again, one-dimensional equation with one variable, kappa, which is 0.5 GeV. And that reproduces all the hadron masses. And then you can put heavy quark, that's for light quarks. For heavy quarks, you put in the phenomenological heavy quark masses. So all the ratios of masses are determined. The value of the proton mass, so it depends on kappa, but that's because we use our GeV convention. So you get beautiful equations for mesons and baryons, eigenvalue equations, which are identical for mesons and baryons. The only thing they differ by is the internal momentum is 1 unit difference. So you again find this meson-baryon degeneracy where the mesons are superpartners of the baryons. And we've checked this out throughout the entire spectroscopy. This is work with Dash and Norsay. And you go through this and you get these beautiful Regge formulas and formulas for light front wave functions, which agree with phenomenology, the form factors. In the case of the pion, you get a zero mass pion if there's no input quark masses. That's one of the solutions. And you get the complete spectrum. The m squared is equal to 4 kappa squared times the quantity n plus j plus L over 2. And that really is textbook. This is actually just like hydrogen physics in atomic physics. And you also get the analytic form for the light front wave functions. You also see a superconformal algebra. This is mesons, which are quark antiquarks with baryons, and the tetraquarks. And you get Also, so you go from mesons to baryons, and from the baryons, you can replace from the quark diquark, you replace the quark with another diquark, and now you get two diquarks, and that's the four quark systems, which are the diquarks. So then you go back and you see, in fact, the universal Reggie behaviors, and you can also get the tetraquark spectrum, as well as the light front wave functions and the massless pion and all the things I talked about. And you get this super conformal algebra, which relates mesons to baryons to tetraquarks. And you get universal behavior in the kinetic energy terms, universal behavior in the potential, and so on. And there's a very old theorem. So supersymmetry, which is built in between the meson baryon spectra, has really been a hidden symmetry of color SU3 in physics. You don't need squarks or gluinos. It emerges from this light front holography and color confinement. And you get beautiful Reggie spectrum, as I said, degenerate behaviors between the rho omega trajectory and the baryon trajectories. It's the whole formalism is relativistic, frame independent. The QCD mass scale appears with a unique light front potential. You get the spectroscopy dynamics of light quark hadrons with one parameter. You get the zero mass pion. You get the universal Reggie slopes in N and L for both mesons and baryons. And you get the same splitting, this parallel trajectories. You don't actually, some people think that you get a breakdown of chiral symmetry at high momentum. It doesn't break down. You just see this, it goes on. And you get the phenomenology of light front wave functions, form factors, all the electroproduction exclusive processes, and you can extend it to heavy quarks. So the underlying principles is number one, Poincare invariance. You're independent of the observer's Lorentz frame because you're quantizing, like Dirac said, fixed light front time tau. You have causality, information only within the causal horizon. That's light front physics. And again, I emphasize that instant form violates causality. Light front holography, where you have this amazing resemblance between the fifth dimension physics of ADS5 in the variable z in the fifth dimension with the variable zeta in our world, where zeta squared is b per squared x1 minus x. You have a mass scale kappa, which is the only way you break conformal invariance of the action. You have a dilaton in the fifth dimension, e to the plus kappa squared z squared, which is the color confining potential in our world. U of zeta squared is kappa 4 zeta squared. And you get the superconformal algebra, which relates mesons to baryons, which are quark diquarks, and tetraquarks, which are diquark antidiquarks. And if you look again at all the different theories, you see, in fact, the data is universal slopes in N and L, and you get beautiful light front wave functions, which have, if you go in N, you see the wave function crosses 0 N times, and so on. So you understand the wave functions and beautiful results for it. And you also get the distribution amplitudes and light front wave functions. So yes, am I about through now? I'm not watching my time.
Yes.
Can you
You
hear me?
have 5 more minutes.
Okay, yes. So you get light front wave functions, which actually have a very simple form and distribution amplitudes. The distribution amplitude for the pion, for example, is just 4 over root 3 pi times f pi, the pion decay constant, times root x1 minus x. And that reproduces virtually everything we know about mesons. It's rather startling how simple this is. And the value of f pi, the pion decay constant, is related to kappa through the formulas. The light front wave function itself is a Gaussian in k-perp. It's e to the minus k-perp squared over x1 minus x with a factor 2 kappa squared downstairs. And an overall factor 4 pi over kappa root x1 minus x. So this is really remarkable. You get one of the things that's very beautiful is Forshaw and Sandepan use the holographic light front wave function for the rho meson to calculate diffractive rho electroproduction. And remarkably, the description that you get for the diffractive rho electroproduction cross-section just goes right through every data point. It's rather remarkable. And you get sigma L over sigma T because you can vary in the case of the cross-section, you can vary the virtual photon polarization and get the ratio of L over T. And all this comes just from one light front wave function which is psi of x in k perp is 4 pi over kappa root x1 minus x times a Gaussian in k perp squared over 2 kappa squared x1 minus x. That one wave function is the solution. It's a lot analogous to the Bohr theory of atomic physics, where you get so much from just a simple ordinary Schrödinger equation. Here we have the light front wave function equation. And we get these beautiful light front wave functions, and which actually not only work in the initial state, but in the final state. And so this allows you to compute hadronization at the amplitude level. So when you produce a jet, and so in the quark and antiquark produce a meson, the light front wave function actually gives you, in fact, the hadronization probability at the amplitude level. And everything's boost invariant. You're connecting the confined quarks and gluons to hadrons. So again, just as a summary, we have a theory which has got color confinement, and we have the analytic form of the confinement potential. You have all the conformal properties of QCD built in despite the mass scale. You have a massless quark-antiquark pion bound in the chiral limit. You have QCD coupling at all scales. I didn't discuss this, but you actually describe what we know from phenomenology, the QCD coupling alpha strong at all q squared, all space like q squared. And that comes from what's called the Bjorkian sum rule, where you actually measure directly the QCD coupling at all scales. And then you have the connection between perturbative and unperturbative mass scales, everything Poincare invariant. You get the hadron spectra, Regge trajectories with universal slopes in N and L. You get supersymmetric fourplets, meson baryons, and tetraquark supersymmetry. You have their light front wave functions, form factors, structure functions, hadron observables. All the counting rules are obeyed. You get hadronization at the amplitude level as the quark jets and gluon jets become hadrons, many phenomenological tests, and it's systematically improvable with the basis light front quantization, and that's using the methods that James Very and his group discussed. So this is really a remarkable supersymmetric features of hadron physics. And again, if you look at the data, you see that in the strangest sector that the kaon and lambdas, the kaon mesons and the lambda baryons are degenerate. If you plot this amazing thing, but relation between LM and LB just by 1 unit. And it works for the D mesons and the lambda C mesons in the case of the charm sector. That works perfectly. And you get the tetraquark spectrum right, and you get superconformal algebra. You get the structure of the F2, delta, and A1 meson all together as a superconformal fourplet. And that's, again, tetraquark physics. So you have superconformal meson baryon tetraquark symmetry, which is gorgeous and comes from all one masterful equation. And if Marina Nielsen did a heroic job, she went through the whole particle data book spectrum, and she looked at the meson baryon tetraquark and saw that, in fact, you can organize the whole hadron spectrum using this formalism I just discussed. And with the super partners, also with one charm quark, everything works beautifully. Beautiful agreement. So you also have all the tetraquarks and how they line up as Regge trajectories. That's very beautiful. You have a harmonic oscillator potential kappa 4 zeta squared. But if you go to heavy quarks, 2 heavy quarks, it becomes just constant times r. So in fact, this kappa 4 zeta squared in 3+1 physics is in fact the same as the linear potential we're familiar with for heavy quarks. And this is work that Travinsky, Gwasek, Dash, and Determan and I did. So again, you get these light front wave functions. They're invariant or boosts. There's remarkable insights from ADS QCD. You get all the form factors just from the overlap of light front wave functions. And you get, if you plot q squared times f pi, it goes right through the data. If you look at the time-like, you can actually understand the time-like structure as well from the pole structure on the time-like side. And that works very well too. And you see, in fact, the combination of the twist 2 and twist 4 contributions to the meson, and there's a 14. The fit shows it's a 14% probability for the 4 quarks in the meson pion. And you can plot the meson and baryon the time-like and space-like form factor together get one universal picture, which unifies the JLab data on the space-like and the Babar data for the time-like pion form factor. And for the case of the baryon form factors, you get Q to the fourth times F1. The Dirac form factor is constant. You see that right for the protons. But one thing that's very unusual that we're still puzzled by, you get the neutron poly form factor dead on, but the Dirac form factor is off. The points around Q squared of 4 J squared are too low experimentally. And that's about the only place where you see a radical departure from the prediction. So people should redo that experiment. That is the Dirac form factor of the elastic neutron proton form factor. And there's a beautiful formula for the Pauli form factor overlap of light front wave functions, where you get a spin difference between SC equals minus a half and SC to the plus half, SC to the minus half in the initial state, SC to plus a half in the final state. And you actually derive the non-zero proton anomalous moment and its internal non-zero orbital momentum that comes from this physics. And you get this, again, the Pauli form factors and so on. And then, as I mentioned before, if you use the Bjorkian sum rule, which is the integral over x of the G1 inclusive structure function to spin-dependent structure function, that integral gives you 1 minus alpha G1 of Q squared. It gives you a definition of the QCD coupling at all Q squared. It's well measured, has asymptotic freedom at large Q squared, computable at large Q squared, perturbed QCD. It's got the universal beta 0, beta 1, which is a theorem, and you get analytic connections to other schemes in what's called commensurate scale relations. And then if you look at the data for the Bjorkian sum rule running coupling, alpha strong, it actually looks just like the data in low Q squared. In fact, it's besides asymptotic freedom at large Q squared, at low momentum, the running coupling is pi times an exponential minus Q squared over 4 kappa squared, where again, kappa is that universal mass scale I introduced before. And if you look at this, you see a beautiful transition between the space-like, the low Q squared and high Q squared QCD coupling. You know, we always talk about asymptotic freedom. We rarely talk about the low Q squared dependence of alpha strong. And it's just a Gaussian, either minus Q squared or 4 kappa squared. And the Gaussian matches the perturbed QCD at a Q0 of 0.87 GeV, plus or minus 0.08. So I think I've talked way too long. I'm sorry I didn't show the slides. It's really terrible. But you see, in fact, the distribution of the quarks and the proton. I have slides on that. The U quark, the D quark, the polarization contributions, and so on. I think it's really remarkable that you get so much from this very simple holographic light front QCD. And I'll stop right there. So I'm very happy that I could speak at this in honor of A.N. Mitra, his memorial symposium, and I'm glad I could meet him, and I think he would be very much like the content of my talk today. Okay, thank you. I'm happy to take questions.
Thank you,
And I
Professor.
apologize that I gave it all orally. Yeah, I don't know if it's sensible or not. Who knows? Do you want to comment?
Thank you, Professor Sten, for very, very interesting and enlightening talk. So maybe
Thank
we
you.
can have only one question.
Hi.
Yes, Professor Kaushal.
Here, R.S. Kaushal from Delhi University, Professor
Oh,
Brodsky.
good to meet you.
Yeah. Some time back, there were speculations about pentaquark baryons and tetraquark mesons. There were speculations about pentaquark baryons and tetraquark mesons.
Oh, the pentaquark mesons, is that what you said?
Baryons,
Yes.
yeah. Pentaquark baryon, yeah. So what the current status?
Yeah, so not the
Experimentally.
world's experimentally, there's, we use the data that's in the particle data book to identify all the tetraquarks. And you're asking about pentaquarks too, right?
Yeah.
And there's still more work to do that. And this, you can do things like, for example, diquark, quark bound states, and use this formalism, use this confining potential, and so on. We haven't done that, so I hope you'll look at it.
Yeah, I visited you sometime back. Yeah, if they are there, how your sum rules will work for them?
They should work. Yeah, it
should
work. Yes, I agree with you. That's right.
Now, I think Is that all right, Professor Kaushal?
So please
Yeah,
look at
thank
my,
you, thank you. Thank you, sir.
Because
I
now
hope people will-
I can see my time, it's 9:42, so
Yeah.
we can move on. So thanks once again, Professor Stan and Professor James for your very interesting and enlightening talk. And now I transfer it to Professor Amitabh Mukherjee. So over to you, Professor Amitabh Mukherjee.
Okay, I'm sorry about my slides, and people should try
Yes,
to
we missed
please
your
post them.
slides. Beautiful
Please post
slides.
them, and then people look at them.
Yes,
Okay.
yes.
I don't know why it didn't post correctly.
But
Okay, thank you.
we could get the entire philosophy behind the calculation.
Oh,
Yeah.
good. That's good. Okay, maybe that's even better.
Yeah.
Okay, thank you. I'm glad
I
you-
think the slide can be uploaded and we can use later on.
Thank you. Okay. You said you do have them then, is that right? Yes. Okay, great. And maybe, I think that might be useful for people, just review those slides and you'll see that it matches my dialogue.
Yeah, that should be possible. We should certainly be able to upload the slides as well. That's a great
Yes.
suggestion, Nimai.
Yes.
Okay.
Thanks. Wonderful talk,
Thank
Professor
you.
Brodsky.
What is your name? I'm sorry. Hi.
I'm
that-
Gargi.
Good to meet you, Gargi. Okay. Bye-bye.
Okay, so unfortunately, I have some bad news at this point. It seems that the next session, which was supposed to be having Professor Naresh Dhadij and Professor Mohammed Sami, is going to be unfortunately scrapped because of some unavoidable reasons. And so I apologize to our chair, Professor Amitabh Mukherjee. Very sorry. There has been some issues apparently. So I think we are therefore headed to, let's see, as per the schedule, just a moment. So we have Professor Indranil Mazumdar scheduled to speak 45 minutes from now. And I think perhaps we could have a coffee break, an impromptu coffee break of sorts as of now. And this link is going to be the same. We are going to be here and we reconvene at 10:25-ish for the session to be chaired by Professor Bhasin. And with speakers, Professor Mazumdar and Professor Chaudhry, Pradesh Chaudhry. And sorry for this, apologize.
Just one suggestion, Alok, because Professor Mukhopadhyay is there, maybe he would like to say something.
Yes, absolutely. Professor Amitabh Mukherjee, by all means, it'll be so beautiful, so nice. If you may wish to say something, it could be like, kind of a part reminiscence session and a part impromptu technical talk. I mean, we would love that. It'll be a blessing. It's certainly a blessing in disguise, I would say, if nothing else.
Absolutely.
We leave it to Professor Amitabh Mukherjee, please.
Is he speaking? I think he's muted.
Professor Amitabh Mukherjee, you are muted.
But have been unmuted.
No.
Okay. Can you hear me now?
Yes, yes.
Okay. As I said, this 45-minute slot is a long slot to fill, and I won't even attempt to do that. And I won't try to uh, give part technical and part reminiscence talk because that won't work. So if it's all right, I just give some brief account of my association with Professor Mitra. Is that all right? All right, Alok?
That'd be beautiful. Absolutely. Please, by all means. Thank you.
So I was an MSc student in Delhi University, and Professor Mitra taught me two courses in MSc final. At that time, the course structure that was prevalent then, these courses were called Advanced Quantum Mechanics and Introduction to Quantum Field Theory and Quantum Electrodynamics. A bit funny, the title of the second one. Those were the two courses that he taught. Both of them he taught to full houses. Much later, I came to know that people who were not in that section, who were not supposed to be attending, were also in the room. That's why the room was always full. Okay. That's something I came to know years later from a classmate. So, Professor Mitra always came to class without any piece of paper in hand. He would ask, where were we last time? And somebody from the front benches would prompt, and then he would just continue from there. So it's not just that he had this thing. In fact, once when he got stuck, he said, yeah, when she's all in my head. So it was all in his head, and he could do that. But more than that, once what happened was that he asked some general question, and unfortunately, several people in the front row gave the wrong answer to this question. Some of us who were sitting far back had the right answer, but we were not heard, and the front benches prevailed. So he was really perturbed by the widespread misconceptions about basic mathematics. So he said, well, it's pointless talking about quantum field theory right here. What this class needs is a class on advanced linear algebra. And on the spot, without preparation, he switched to this 3-lecture mini course on advanced aspects of linear algebra. And just like that, I mean, what one would want to do is, okay, let me just look up some book. No, he didn't do that. He just started and went on, continued until he was satisfied that he had covered the topics that he wanted to do, and then resumed talking about advanced quantum mechanics and field theory. So his classes were always for those of us who are going to continue in physics. I must say that the big classes in Delhi University's MSc program had started. So a majority of us who were students were not going to become physicists. That started from the batch of the batch senior to mine. I see that Amitav Rai Chaudhary is here. From that batch onwards, we had these big classes approaching 200 students. Of course, these days it's 400 plus, but most of us were not going to become physicists, but those who were going to become physicists, and they would never miss a class of Professor Mitra, or Mitra Saab, as he was called. And um, they it was not a matter of a good set of notes. That was not what one that was not the takeaway from Mitra Saab's classes. It was that inspiration, the feeling that there is a subject that needs to be learned and that deserves to be learned and can be learned by us. So this feeling was what came across most clearly through these 2 semesters of classes with Mitra Saab. As it happened, 12 years later, 12, 12 and some 12 years and something later, I returned to Delhi University to teach, and so became his colleague. And during this time, we just taught one core course together, as it happened, which is electromagnetic theory. Um, there, uh, um, there could have been other opportunities, but meanwhile, the syllabus had changed, and those two courses that he had taught, where I could have joined him, those no longer existed as core courses. They had been replaced by a course called radiation theory and by a different course. So we taught electromagnetic theory together, and there were four of us, and four sections, each with a different teacher. That's what happened those days. So mm, uh, we joined together and coordinated. But that was the last last academic work with Professor Mitra. Unfortunately, after that, we never collaborated or even had extended physics discussions after this particular game theory course. So in the later years, of course, he retired um, a few years after this, so the years were not many. But I didn't have the opportunity to interact with him. But basically, what I took away from my master student days, that remained with me as uh, that the impressions or memories of Professor Mitra, uh, more than our infrequent or brief interactions as colleague. It was the student. It was so you could say that I'm his student, in short. So I guess that's about it. And now, what? So what's the resumption time? Hello, Kornemai, somebody?
Well, we can continue for as long as you want, because the next talk is actually at 10:30.
Uh, okay. No, I have said what I had to, but let me talk briefly about um, uh, some directions that happened after that, those master's days, um, and which is related to both the speakers who are absent. Okay, so I started immediately after that. After my Delhi University masters, I went to TIFR as a PhD student and worked in the area. Um, I was basically going to work in theoretical particle physics, and I worked in classical field theory at the time. Years later, after returning to Delhi and beginning to work with my collaborators, such as Professor Panchapakeshan, who's here, I kind of switched fields to astrophysics and cosmology. And that brought me into close contact or some sort of contact with both the speakers who are unfortunately missing today, Professor Dadich. I was in a group of people who were the first participants in the first workshop hosted by IUCA in 1989. And Professor Dadich was one of the founding members. Later, of course, he's known, I mean, people identify him as former director of IUCA Pune. But I think equally importantly, he was one of the founding members who helped to build up the organization and keep it going in the early days when it functioned from a shed, actually. the grand building, prize-winning building where Ayuka stands now, came up much later. At that time, Pune University had given some rooms to Ayuka, and it was literally a shed, place where our workshop was held. So Professor Dadij braved it through those days, and he was always a maverick and has been, continues to be. I was in fact looking forward to his talk. It was bound to be something challenging contemporary majority views. So he has always been doing that. It's a pity that I can't hear him today. The other speaker today, Professor Sami, is my contemporary. Okay. A couple of years younger, perhaps. We got to know each other well when we were both teaching in Delhi. I was in Delhi University and he was in Jamia Millia. And we were working on similar things, though as it happened, we never collaborated. What happened was that some people who were my collaborators later collaborated with him. So we had common collaborators but never worked together. Um, Professor Sami has been working in what may be called the present accepted standard model of cosmology. So while one of the speakers is a person who challenges the standard model, the other explores the limits of the standard model. So Sami has been doing that and very successfully. He is one of the leading Indian cosmologists of our generation. The kind of cosmology where we actually confront things with observation. Sorry, and not merely theoretical model which have no interface with observation. So Sami has been very successful in doing this, and having had a long innings at Jamia, he's now enjoying his second innings at SGT University. I wanted to say this to him face to face, but again, unfortunately, he's not there. So we continue to have a second order interaction, so to speak. I'm sure this language is perfectly appropriate here in this gathering. So we continue to have people who interact with both of us and who are collaborators or possible collaborators. And maybe one day we'll collaborate directly, but we haven't done it so far.
Those are your gluons, huh?
Huh?
Those are your gluons.
Yeah, those are gluons.
You collaborate with.
Yeah.
I mean, a common collaborator is something like a gluon.
Yeah, absolutely. So I think I don't want to take up more time of this.
Wonderful to see Uncle Professor Pramod Srivastav is has joined. It's great
Yes.
because he's not on the, he's the phase difference between India time and Canada time. Despite that, he's managed to join.
It's midnight now.
Yes, that's amazing.
It must be close to midnight. Yeah.
Would you like to say something, Uncle Pramod?
Well, yeah. I mean, my trajectory with Professor Mitra has been very different. I was neither a student, nor did I first start as a colleague in the Delhi University. We first met in Bloomington. I came there as a just fresh graduate, just joining at the first research associate appointment, and he came as a visiting professor. And we became to talk because, after all, two Indians in a department, they have to talk to each other. So we started talking, and then by whatever the official thing that the Bloomington University did, Indiana University. We were also our my small apartment and his apartment were also in the same building. And so that we had a very good collaboration as persons, I would say that. And well, then I joined Delhi University, and what he pushed me into teaching electronics. I would say he pushed me in there, and I spent some 20 years in the electronics lab after that. So that's my main interaction with Professor Mitra. And of course, I talked a lot with him. He says if you want to, I mean, that has been, I mean, he has been great. He always said if you want to talk some physics, you go and talk to Pramod. He'll say something about it. So that's all.
Somebody who's raised a hand.
Yes, I myself, I am tempted to say a little bit about sir. So give the permission.
Be such a pleasure to hear you, Nimai. He was so fond of you.
Yes. Should I start?
Please.
So what happened? I joined MSc in 1979 after passing BSc from Ramjas College. Incidentally, in my class, Professor Sanjoy Jain was there, Nivedita was there, Rahul Sinha was there. I still remember many other people also. So the first class, Professor Mitra was teaching us the quantum mechanics. I want to narrate a story of that class. So he was trying to teach Dirac equation. So before teaching Dirac equation, he started a history of physics. What I want to say is that apart from mathematics detail, he knows the history very well, history of physics. He started a Solvay conference where a young Dirac and towering figure Niels Bohr attended. In the tea party outside, Professor Dirac, Dr. Dirac was standing alone. He didn't speak much. So the towering figure Niels Bohr came to Dirac and asked, Dr. Dirac, in which field you are working? And Dirac answered that I am trying to write a relativistic quantum equation. Bohr asked, Klein and Gordon had already done that one. Dirac tried to answer that, no, I don't believe. So then why? Niels Bohr asked to Dirac, and Dirac tried to explain. Then the bell rang and they went for inside the room. So Dirac could not explain why he didn't believe, and they said Professor Mitra started what Dirac wanted to tell to Bohr in the class. What is Dirac's mind, Professor Mitra narrated in the class. That is starting from the analogy from Maxwell electromagnetic equation. From there, we can have first order equation. From there, we can have the second order wave equation, not the vice versa. Like that, in quantum also, the analogy is that we should have a first order differential equation or quantum equation. From there, we can get the Klein-Gordon second order, not the vice versa. That Dirac wanted to convince Bohr, but the time was not allowed. So that Professor Mitra narrated in the classes what Dirac was thinking. It is not in a textbook. So I thought that Professor Dirac was just like Professor Mitra was just like Professor Dirac at that time. In my eyes, when Professor Mitra was explaining, I thought that he is Dirac. So that impression I had in my class. Okay, because the feature is also the same. So another event I want to side is that after having my MPhil and a PhD, I joined Guwahati University long. So after many years, I visited his house, 244 Tagore Park. Okay. And Professor Mitra, after giving me tea and everything, gave me a bundle, a packet. And he told me that after thinking, I have given this thing to you. So when I took and when I opened the packet, I found that there was a necklace of high price. There is a sari also, and there is a letter also. In that letter, it was signed by none other than Bethe, Hans Bethe. Probably Hans Bethe and his wife in early age, when Professor Mitra was young, visited Delhi and they brought that presentation for Professor Mitra and his family. And he kept this thing in the Almira, and I don't know why he is looking for someone to hand over this thing, but still those things still preserved in my house. A necklace, a sari, and a handwritten letter by Professor Hans Bethe. Thank you very much. Okay, it is my
That
reminiscence.
was so nice. Thank you. Thank you, Nimai.
So anyone else? Yeah, Professor Kaushal. Yeah, go ahead, please.
You are muted, Professor Kaushal.
Yeah, now it's okay. Yeah, so corresponding first order equation is Riccati equation, where potential terms appear as a part of KdV equation. So these, well, because he was quoting Dirac about the construction of bringing the relativity in the quantum mechanics. So that is a first order equation, Dirac equation that way. Corresponding to the Schrodinger equation, even without relativity, we have a equivalent equation called Riccati equation. Riccati is a first order nonlinear differential equation, solvable, exactly solvable. And potential terms appears as a solution of some another equation. This is just I wanted to point out here.
Sir, according to him, for Maxwell equation is first order in space and time.
Right.
After we have some algebraic manipulation, we get a second order equation of E and V. But the information is lost. The direction, vector, property, everything is lost.
Yeah, mathematical setting.
That is what he means about. That is the reverse is not possible. That is
Even
what he
even
means
here, the potential term appears in a more complicated manner.
So yes, there is no potential at this moment. Okay, thank
Sorry,
you.
can I interrupt? When is the next program? Is it at 10:30 or 11? Or have Naresh and Sami come or they haven't come?
So, Professor Panchapakeshan, we did not have, unfortunately, the current session, which was 9:30 through 10:30, which was supposed to be having Professor Naresh Hadich and Professor Mohammed Sami. So the session starts at 10:30 as per the former schedule, but we utilized this absence of speakers by requesting Professor Amitabh Mukherjee to kindly speak. So as per the old schedule, we resume at 10:30 with Professor Indraneel Mazumdar's talk, chaired by Professor.
That will be at 10:30. That will be at 10:30, is it?
That is correct. That is correct.
Okay. Thank you so much.
Sure.
Okay. If there's anyone else who wants to speak in this impromptu round, please go ahead. Otherwise, we'll close and reassemble at 10:30.
You, Professor Mukherjee, to have this free session, free and frank session. Yeah.
I see people in the attendees list. I can see people who who did not speak in yesterday's session and who are not slated to speak. So this is their chance if they want to say anything.
Actually, we don't know if
Yeah.
they're
No,
online. They
yeah.
they are
Professor Prabhu
apparently
Srivastava
there,
said-
but we don't know. We don't know. We can't see them. So probably they're logged in and they're just going to come back just before the 10:30 session. But it's lovely to see you, Amitabh. Thank you so much for joining.
Okay, so um, I saw Professor Pramod Srivastava raising his hand,
Yeah,
but probably he
it
was
was
just
quite late for him.
waving.
It was quite late.
Probably just waving by. Okay.
Yeah, I
Uh,
was so glad that he could join because Canada time.
hello, Nivedita. You want to speak?
Is she there?
Yeah,
Wow.
you're muted. Unmute yourself, please.
Okay, thank you.
Oh, Nivedita
I
Tati.
I
Hello.
didn't. Well, I would like to express my gratitude to all of the organization
Oh,
of this very nice memorial lecture and meeting of Professor Mitra, and I would like to express my gratitude to him for being, inspiring, a very important, inspiring personality in my career, actually, in teaching me quantum mechanics and I think it was particle physics and quantum field theory in my master's days, which inspired me to go into this field for my PhD. And I really feel very grateful to him. And he was always inspiring figure. And on a personal note, I'd like to say that he was also my local guardian for a year. And he was a wonderful local guardian. And he used to, on Sundays, sometimes I used to visit the family, and we used to have lunch together. And in a very traditional Bengali style of, the full course meal. And in those days, I was a hungry Miranda hostel student, MSc student. So I used to eat, whatever was given. But I used to miss my favorite parts, which were the fish and the non-vegetarian, the I think the chicken or whatever was being served at that time, in a hearty way, because I used to eat the first part in a very 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 student hosteler way, and I couldn't eat as much as I wanted to all the things that I loved, because I was so full. And he used to be very amused with this, Professor Mitra, and Anjali, ma'am, Anjali ji, his wife, Mrs. Mitra. And I think Gargi was was a little in her skirt and pigtails at that time. And Vani was also around, and we used to have a very nice family lunch actually. And I remember this with very fond memories. So I just wanted to share this much.
Thank you so much,
Yeah.
Nivedita Di.
It was a
You
great.
take me back long time. Back, you've
Yeah, and
taken
it
me back
was.
so many decades back.
Yeah, it was a very warm and wonderful family, and I really appreciate that in my early days you all were there. Thank you. Yeah.
Professor Deo's, my grandmother used to tell me that you were Professor Deo's daughter, and
That's right. Yeah.
there was
Yeah, Daddy and Professor Mitra were
Baba,
friends. Yeah,
great friends.
very good friends. So that was a tie between us. Yeah. Thank you very much. That's all I wanted to say. Some
So
reminiscence.
sweet of you. So sweet of you. Thank you so much, Nivedita Di.
Thank you. Bye bye.
Okay, great. Anyone else? If no one else wants to speak, then Gargi and Alok, shall we take a tea break up to 10:30?
Lovely, lovely. Please, let's do that.
Okay.
Thank you so much, Professor Amitabh. Thank you.
Thank you so much.
वीडियो करना बोलना भी है बोलना यहाँ से है हो गया स्टार्ट कर नहीं बोलने के लिए तो यहाँ करना पड़ेगा ना कर दिया मेरी फोटो भी नहीं आ रही फोटो नहीं आएगी
Hello, my name is Alok. Am I correct that we have
Hello?
somebody with the name Zoom user is Professor Bhasin?
Yes, I'm Basim. I'm speaking from here.
I see. Namaskar, Professor Bhasin. So wonderful to have you on board. So great. So,
Yes,
with your permission, we will begin in 2 minutes.
Okay, fine. That's right. That's good.
Thank you so much.
Is Indranil there?
Yes, I'm there. I have started sharing. Are the files visible? I mean, the slides, the very first one.
Mm-hmm. So,
Your slides are visible, Professor Indranil. Yeah.
Shall we start now?
Just perhaps we could wait for a couple of minutes so that people can come back, because we had announced that the session will start at 10:30. So just a couple of minutes.
Okay.
Thank you.
Professor Bhasin, pranams to you. Thank you so much for being there.
Oh, fine. Thank you.
I was trying to call you.
Just wait.
I was trying to call you. I hadn't seen you on the group, and I tried to call you, and then I joined back. Then I see you here.
Yes, I am here. I'm just trying to see if I can just in the meeting is there. In fact, I have to first of all see.
So, Professor Bhasin, with your permission, perhaps we could start the session.
Yes. Okay. Fine. I'll just start it.
Yeah. So, I request you to please start. Thank you. Thank you so much.
Yes, I invite Professor Indranil Majumdar to give a talk on the free body systems. Actually, Professor did see in, and then he joined the Nuclear Science Center for his PhD. He did his PhD under this joint supervision of KP Sinha and myself. And after doing the PhD, he joined Tata Institute of Fundamental Research, where at present he is a full professor in this. He has been in contact with me for so many years, and we have been jointly working on the research problems. He will be talking on the free body systems. I invite Indranil Majumdar to please give a talk.
Good morning, everybody. Thank you, Professor Bhasin. Let me just begin by putting on record my sincere thanks to the organizers, especially Professor Alok Mishra and Dr. Gargi Mr. Delmont for their kind invitation. Just one sentence here before I start the talk, that actually there is a change. I mean, the title of the talk is To Fuse or Not to Fuse, A Tale of Two Nuclei. It is actually heavy ion. I'll be drawing today from my work on heavy ion nuclear physics. So Professor Ashok Nath Mitra was a towering figure in the world of physics in India with an enviable degree of international recognition for his many accomplishments. He was one of my most venerated teachers, and I had the good fortune of enjoying his affection and encouragement from my student days till his last. Now, let me tell you about why I selected this topic for today's talk. A significant portion of my research activities in nuclear physics is centered around studies in structure of exotic halonuclei and search for the elusive Efimov effect. As Professor Hasin just mentioned, we use a three-body model of the nucleus, which is 2-neutron halonucleus, using separable non-local interactions. The use of separable non-local interactions in three-body nuclear physics was truly pioneered by Professor Mitra, and along with his very able students that time. One of them is the chair of the session. So ideally, I should have chosen to talk on halonuclei and Efimov effect. However, the research interests of Professor N. Mitra was a rather broad canvas. And though he was not truly a practitioner in structure and reaction of nuclear physics at the low and medium energy, he always kept himself abreast of the developments. And even as late as 2009, he actually wrote a wonderful piece, India in the World of Nuclear Physics Then and Now. And if you go through that article, you will know that he was totally in command of whatever was happening in the low and medium energy nuclear structure and reaction studies even at that time. And which is why I decided to talk about my activities in heavy ion physics and present you some very recent results, though the work is going on for last at least 2 decades. I'm sure that Professor Sar would have been very happy and enjoyed the fascinating world of heavy and nuclear physics. Now, the very varied nature of the audience and the time limit do not permit me to go into the nitty-gritty details. Rather, I would just like to give you a flavor of what we are doing, what are the real burning issues. And this is a very hot topic in current nuclear physics. So it's basically going to be some kind of a storytelling. So this is basically the organization of the talk, a prefatory comments right in the beginning, why we are so much interested in this problem. And this is primarily an experimental work, which will probably be a slight change from all the talks that you had yesterday and also later in the day tomorrow, today. It is a primarily experimental work, but we carry out very heavy kind of phenomenological calculations for the analysis. So I will briefly talk about the experimental facilities, the very simple-minded facilities that we have at our disposal. I'll give a brief summary, very brief summary of the last decade-long studies from a collaboration between TIFR, my group, and our group from Inter-University Accelerator Center. And then I will draw from 2 very specific cases, 2 very recent papers, and then I summarize and conclude. So basically, as you know, the 60s, as I can say, was the best of the times for nuclear physics. It was also the worst of the time, or rather, the time of our innocence in nuclear physics. So heavy ion physics was not really there in the horizon. It all happened with pioneering experiments of David Bromley and his collaborators. So basically, they did their measurements shooting carbon-12 nucleus on carbon-12. And they really didn't have anything specific in mind. They just had a machine they built and they wanted to test it with heavy ion beam, which was not available those days. So they were expecting certain kind of results, but lo and behold, what actually happened, they saw distinct resonance structures, as you can see on the right side of the panel. And these basically, when this was analyzed and understood primarily by the theorists some from US and some from Germany, by Walter Greiner's group, they realized about what actually is happening. And in a sense, the experimental discovery and theoretical description of nuclear molecule led to the development of the modern heavy ion physics. So now this particular plot is very, very important. So what actually we are doing? This is for those who may not be involved at all in heavy and medium energy nuclear physics studies. So we want to understand the real-time response of the nucleus at hot and rotating nucleus to an external trigger. And this is basically done by shooting a heavy ion on another heavy ion, as you can see on the right side, this pictorial depiction. And then many things can happen. It can undergo an elastic scattering. It can undergo a mild inelastic scattering. It can undergo some kind of transfer reactions where few nucleons can be moved from one side to the other. Or it can just, as you can see in the second part, it can just form a dinuclear system, which may rotate a bit and then fragment immediately. This is what is called quasi-fission. But it can actually fuse and form so-called the mononucleus, which, because of a critical angular momentum, doesn't really see the barrier, which has vanished at that angular momentum, and split immediately. This has been termed as fast fission. However, if the system fuses and survives this fission and fully equilibrates in all degrees of freedom, then 2 things can happen. The system is now inside the pocket of the potential well in the potential energy surface, and then it can split into 2 parts, which is called fusion followed by fission, or the system can survive fission and it's a hot system, so it will evaporate few particles and shed all its energy and come down to its ground state. So what we have there called the evaporation residues. And if you detect experimentally evaporation residues, you know the system has survived fission. That is the moot point, actually. So the important thing in the analysis is the dynamics of the formation, dynamics of the decay of the system, as I just said right now, evaporation of particles or fission. And then in the analysis, you actually have two-pronged approach. You have to have statistical theory. Without that, you cannot do anything. You cannot find out how the particle evaporation is happening, etc., which is governed basically by phase space, Bohr's theory, and also governed by the nuclear level density. However, dynamics is of paramount importance, so we also have to do dynamical calculations. Mind it, nuclear fission, to do it fully microscopically and considering quantum mechanics, everything, is a horrendously difficult task, and the task which is still in progress. So we basically try to take a middle path of a mixture of microscopic, macroscopic approach. Now, the major challenge in the physics is that in this talk, I will be concerned only with the fusion followed by fission and try to see if the system survives fission. But even if you talk of the fusion, you will see there is physics all along the energy scale. If you are below the barrier, where classically you do not expect the system to fuse, it still fuses. And it is much more than what you would have imagined from simple model of simple calculations of barrier penetration, tunneling. Because there are lots of quantum mechanical, this is a quantum mechanics, a lot of channels gets coupled, and this channel coupling leads to the reduction in the barrier, and that leads to the fusion. But if you go to even below the barrier, very, very below the barrier in the region of nuclear astrophysics, there, of course, these couplings gets weakened, and you see much lower fusion. And of course, in my talk and in my own research activities, I am principally involved at a fusion much above the barrier to understand the hot nucleus. So the equilibration and the stability of the compound system, what role the shell effects are playing in this, and the role of complete and incomplete fusion. This is very important as far as our own results are concerned. Role of entrance channel mass asymmetry. If you produce the same compound nucleus by two different target projectile combinations, by the classic Ghoshall's experiment, you may tend to believe that the system will decay exactly in the same way, but they do not do that. So there is a role of entrance channel definitely, and the role of nuclear level density, barrier height, the fission barrier, which is definitely a dynamical quantity, depends upon the spin and the temperature, and the nuclear viscosity. So basically in our work, we have been involved to understand this dissipative mechanism in this heavy and induced fusion fission processes. So the primary motivation is, of course, twofold. One is to understand the dynamics of the fusion and the subsequent fission or survival against fission. And the second, which has always been the holy grail of nuclear physics, the quest towards the formation of super heavy elements, because you want to form a very heavy system, very high Z value, but it will fission. So if you know somewhat the lower masses, what is the dynamics, we can plan for super heavy elements. So experimentally, this is achieved by measuring the fission fragments. Since it is fissioning, you talk about the fission fragments. Then we measure the evaporation residues, and we measure the charged particles. We measure the neutrons and GDR gamma rays, which is giant dipole resonance gamma rays. And once we get the data, we analyze it. And in that analysis, we basically try to see how the nuclear level density, the shell effects, the entrance channel masses, the target projectile deformations, the barrier heights, which is spin dependent and temperature dependent, and the nuclear viscosity, and above all, their dependence on temperature and angular momentum. So basically, these two slides sum up what I want to do. Now, nuclear fission, as you know, is an evergreen process. It is basically large-scale mass transfer across a barrier in a dissipative medium. And it's a very, very complicated process. Either you study through microscopic analysis or you try through microscopic analysis. But basically, a middle path has been struck, which is microscopic plus macroscopic. And here are some of the important references, but not exhaustive. So let me just give a quick glimpse of the experimental facilities. As I said, the system is primarily fissioning. So fission fragments detection, that will be low-hanging fruits. So we have fission fragment detectors all over the world. People have charged particle detectors, neutron detectors, high-energy gamma detector, giant dipole resonance gamma detector. In the early days of my work during Stony Brook, my postdoctoral days, we measured a lot of high-energy GDR gamma rays, giant dipole resonance gamma rays from a fissioning system. But the difficult challenges are to measure the evaporation residues. This one has to appreciate and understand because the system is primarily fissioning. So you have to filter out those which have survived from the main beam particle and detect and measure their cross sections. At the same time, since it is all about the game, about how things depend upon temperature and angular momentum, we would like to measure the angular momentum of the fissioning system, which we measure by low energy gamma ray multiplicity detector. So keeping this in mind, so we designed and built a very nice 4-pi spin spectrometer to measure the angular momentum of the nuclei, and that was transported and coupled to the recoil mass separator at Inter-University Accelerator Center. And we did a lot of measurements, and I shall be primarily drawing from our efforts to measure the ER cross sections using gas field magnetic separator HYDRA, hybrid recoil analyzer, and evaporation residue getter spin distributions using TIFR 4-pi sum-spin spectrometer. So this is the 4-pi sum-spin spectrometer in its full glory in my lab, right where I am sitting right now. And this thing, when it is on the beamline of the TIFR Pelletron facility, and it is measuring low energy gamma rays along with in conjunction with the high energy giant dipole resonance gamma rays. And when the same thing has been transported to, this is just the Monte Carlo simulation of the response of the spin spectrometer. I need not go into the details of it, but this is the most of our experimental facility, where you see now this 4-pi spin spectrometer is dwarfed by this huge beast, which is more than 10 meters. This is the hybrid recoil analyzer at Nuclear Science Center. So the nuclear reactions are taking place at the center of this 4-pi spin spectrometer in this sphere, and the evaporation residues are filtered out through these combinations of electromagnetic devices, and they are brought at this focal plane where you see MWPC is written, multi-wire proportional counter. And in addition, in coincidence, we measure the number of the low energy gamma rays from which we find out the angular momentum. So this is basically the experimental setup, and I can tell with a fair amount of satisfaction that this combination of recoil mass separator along with 4-pi spin spectrometer is possibly the only of its kind in the world, and we have generated enormous amount of very interesting results. So what we have tried to do by these measurements, we have tried to understand the role of shell effects, whether shell effects play any role in the survival of the nucleus or its fission, role of entrancewell mass asymmetry, I talked about it earlier, role of the barrier heights, and role of the fusion-fission hindrance, which is some kind of quantum viscosity. So a lot of work has been developed, come out of this contribution, of this collaboration, and all these systems are here. I have actually no time nor intention to go into the details of this measurement. I would just like to summarize that what have we learned from these measurements. So a large number of systems have been studied and a large body of new data, especially spin distribution data, have been generated. What do these measurements and results tell us beyond the obvious interpretations? So what they tell us is this. It's a very difficult ballgame, and it's so there are a lot of uncertainties with the different physical observables like barrier height, nuclear level density, viscosity, etc. So we need there is a need of reducing the parameter space to have a put realistic limits in the statistical model calculations, to carry out systematic analysis of global data, fission fragments, evaporation residue, neutrons, charged particle, high energy GDR gamma rays. Please note that no one group does all these measurements. So it should not happen that for the same system, different groups do different measurements, and with different codes they analyze and they arrive at different results. That is not acceptable. To arrive at the similar conclusions while using different phenomenological approaches, to reproduce the data with the same set of parameters irrespective of the analysis package. So that is basically what we have learned. So with this, I just want to draw from two very recent measurements which have been done in the last 2 years, and I will just try to talk about them. So what are those systems we have tried to study? We have tried to study two nucleus. One is a heavy nucleus, 186 platinum, by bombarding 32 sulfur beam on 154 samarium, and the other is a very heavy system. It is 32 sulfur plus 208 lead forming 240 californium. Why you want to do this? What is the primary difference between them? You see, if you look at the heavy system, it's a heavy system, so it will undergo fission, but it will also survive fission. So some of the cross sections will go into the evaporation residue channel, and that basically means I am probing both inside and outside the saddle. It will be clear shortly what I want to mean by that. In the potential and resources, there is a barrier, and then there is a saddle inside the pocket. The system gets trapped inside the pocket, and while fissioning is splitting, it moves on top of the saddle point and moves toward the fission point. So in this kind of a heavy system like 186 platinum, the system is both inside the saddle and outside the saddle. However, for a very heavy system like 240 californium, it is almost entirely fissioning, 99.99%. And therefore, I am basically probing only the saddle to the fission path. So this way, I can actually see the dynamics inside the saddle and outside the saddle and try to see whether the viscosity that we are trying to study is different in these two different parts. So this is clear from this picture, as I was trying to say. This is a very simple-minded one-dimensional projection of the potential energy surface. The nucleus is a compact object inside the pocket. It moves the flux towards the saddle point. It assaults the barrier and then rolls down at the scission point. It breaks into two. This is basically the thing. So now let us show me some of the results from the sulfur from samarium nucleus. We need not go into the details. These are very involved measurements. And you can see on the left side in the table, a lot of beam energies above the barrier at which we did this, carry out this measurement. And then on the right side, this two-dimensional plot, you can see a blob. This is basically the focal plane of this hybrid recoil analyzer where we have detected the evaporation residues, and from that we can find the cross-section of the evaporation residues after putting suitable efficiency corrections. And we also measure the angular momentum, the spin distribution of the nucleus. And finally, on the right side, on the bottom, you will see the cross-sections. These are absolutely new, fresh data. This have not been done before. So we get the cross-section. So when we get the cross-sections, we have to do the analysis and understand what actually is happening. So the first thing is that without jumping on a model-dependent calculation, there is something which should come out straight away in a model-independent way from just the experimental measurements just after the data reduction. And that is a very interesting thing I show you here. You see on this plot, the red points are our measurements, which have been done for the first time. But the same nucleus, 186 platinum, was also populated some years ago by another group, also from India. We was not knowing that time. And then they measured, but their target projectile combination was very different. Highly symmetric compared to our asymmetric system of sulfur and samarium. It is 48 titanium plus 138 barium. And you see the distinctly at least order of magnitude different in the evaporation residue cross sections. So this is one very important thing, and it shows the clear demonstration of the role of entrance channel in the mass asymmetry. Now we want to go ahead and do the analysis using whatever is at our disposal. So basically, as I said earlier, it's a two-pronged strategy. We use statistical model analysis, and also we do dynamical model analysis. Now, I am talking about some very simple things here. The things are rather, we have developed a very involved statistical model code, but I'm just talking of the basic fundamentals of it. So we in the calculations, we do not do the calculations for the spin distribution of the cross sections. We put the real experimentally measured values, because as you have seen, we have measured the cross sections, so we know the cross sections, and this fission cross section plus evaporation residue cross section gives me the total fusion cross section, which we put in the calculations. We put the spin distribution, which we have measured in our experiment using the TI-4 pi sum spectrometer. We try to take care of the nuclear level densities using a very realistic formalism. We include viscosity, but that is more or less by hand. And we try to look for the temperature and spin dependent of the barrier height. And then once we do that, all these things have been also shown in our earlier work from Stony Brook Grace, which in somewhat recent time I have summarized all this in this paper, in the Pramana paper. And so I want to just show you that this is the spin distribution. This is the spin distribution experimentally we have determined from our analysis. Then you put a gate on different angular momentum domains, and we try to do the calculations. And these are the different formalisms from the level density, temperature dependent and spin dependent level density formalism. So as I said, there are various parameters. I mean, that barrier heights, there the viscosity, etc. So one should not actually try to just feed the data. One has to really see what are the different weight factors that you can attach to the different things, because all of them are playing a role. In this particular case, I'm trying to feed the data or reproduce the data by varying the barrier heights, and you can see we can do that fairly, but we also know what is the error associated, and that is associated with the width of these barrier heights that I show in the plots. Similarly, once that is done, I try to play the viscosity, and you can see what kind of viscosity value that we are getting. So at this stage, we felt that we also do some dynamical calculations. These calculations are primarily done by one of our collaborators from Russia, Professor Avazbek Nasirov, what is called the DNS model, or dinuclear system model. This is a pretty involved model. But one very important thing that I want to draw your attention to in this is that it turned out from this dynamical analysis that incomplete fusion also plays a role. What do you mean by that? You look at the cartoon. 18 oxygen is being bombarded on 93 niobium, and we are talking as if 18 oxygen will fully amalgamate with 93 niobium. But that doesn't happen. One particular channel is that maybe a little bit of tweak, one particle, maybe an alpha particle goes out of it, and the final compound nucleus is not 111, but 107. So in the calculations and while we reproduced our data, it was found that this kind of role, a little bit of incomplete fusion channel, also plays a very important role. So these are some of the potential energy surfaces, and I need not go into the details of this. But the important part is this, that you see on the top, you have the spin distributions, which have been reproduced by these DNS calculations. And you see here, the experimental data is beautifully reproduced by the solid black line, which is the dynamic model DNS calculation. Now, the important thing is that if you only consider complete fusion, that is, no incomplete fusion is happening, then you can reproduce the data to some extent up to 140 MeV or so, but after that it doesn't. But as you switch on the other possibility of a little bit of incomplete fusion, that is the red line, then lo and behold, if you add them up, you beautifully reproduce the data. And trust me, we have been able to reproduce other data also by this. Now, what does it mean? So far, I was going on the premise that a full fusion takes place and then the fission is happening. Or fission is not happening, we are producing evaporation residues. But we have seen a little bit of incomplete fusion, that amplitude also plays a role. So we have to then, therefore, not only the evaporation residues, we should in a future measurements try to measure the charged particles also and do a full kinematical analysis to prove beyond doubt that this DNS model is correct. So this is one of the most important takeaways that we have shown in our paper very recently. And the last part, and I guess I have still some time. So what I'm talking, I will just go and to the very heavy system, which is 240 californium. Now, this system, unlike the previous system, has been studied earlier. I, during my postdoctoral days, studied it to understand the giant dipole resonance gamma rays from this heavy system. Actually, 30 years ago, Bierger-Bach and Mary Tang, they had exhaustively studied the fission fragments because that was the low-hanging fruits. But the evaporation residues were never been studied. In our studies of this nucleus, where we measured the giant dipole resonance gamma rays, we actually found a certain value of the so-called Kramer's viscosity parameter. And I was always intrigued to see whether if we measure the evaporation residues, which is a much, much more complicated problem for the obvious reason, it's a very low cross-section, then whether we can actually produce the data by the same viscosity parameters. And so by viscosity a little bit, so these were our very early measurements of GDR decays, and where we try to find the viscosities parameters by measuring the GDR gamma rays in coincidence with the fission fragments. And we realized that most of the gamma rays are coming basically from the saddle position point. And this is basically the Kramer's formalism. I will quickly go through that. As you can see, from the left, the nucleus, the flux is assaulting the barrier, and then it rolls down. And then you can calculate by Bohr's principle, Bohr theory. But actually, it was a pioneering work, went unnoticed for 40 years by Kramer, who actually showed that basically the width can come down because of the so-called viscosity, which of course he treated classically. But then we have tried to implement this kind of thing with more modern dynamical approaches, like this kind of a transient effect, which depends upon the barrier height and the temperature. That means if the temperature increases, most of the flux of the compound nucleus will straight away go onto the saddle and will not remain in the pocket. So anyway, these are basically just some of the glimpses of the underlying theoretical analysis that we carry out. But I will just say that also the important thing, what is this viscosity? What is it, a one-body mechanism or a two-body mechanism? If it is a two-body mechanism, then you can imagine that it will have a strong temperature dependence. And if it is a one-body mechanism, it is basically like the two system is fissioning, and basically the nucleons, one body is colliding with a moving potential well. So these are some kind of phenomenological approaches to understand this thing, and they will have different dependencies, and one body viscosity will not have much temperature dependence. So we just try to do these measurements. I am almost at the last minute of my talk. And then we bombarded sulfur on 208 lead, and we produced 240 californium, and we just, as you can see, this very, very small little bit of data which is there. This is a very, most of it is almost fissioning. And if we extract after all the efficiency corrections, we actually get the cross sections. But as you can see, the error is associated, is quite large, and we definitely want to carry out these measurements in more detail with a longer beam time in future. So that brings me at the end of this talk. It is a pleasant duty to collaborate, to thank my close collaborators. This is a picture of Ranjan Sarial, who is my former PhD student, who's this work, what I said, from the kernel of his PhD work, and now he's a postdoc at Gran Sasso, and also to my collaborators from Inter-University Accelerator Center and Punjab University, and my long friend and collaborator, theorist, Professor Awaz Begnasirov from Russia. So let me sign off at this point, and I can take questions. Thank you very much.
Perhaps if Professor Bhasin deems it fit, we could now have the Q&A session.
Yes, I think Professor Haridas has a question.
How reliable is this saddle point that Bohr and Wheeler introduced in 39? And are there systematic ways of improving the saddle point approximation?
Oh, yes, of course. I mean, there's been enormous. I mean, I'm happy that you asked. I mean, I couldn't go into all these details there. So what are the on the slides, I was basically showing a single one-dimensional point. But what actually happens that we do multi-dimensional calculations to get the what's called route here, or the potential energy surface. And so it is actually, one should not really think in terms of a one-dimensional barrier. It is a multi-dimensional thing. There are valleys and there are ridges, and the compound nucleus is formed. And this barrier is also continuously kind of under fluctuation because it is a temperature dependent, it's a spin dependent. So basically, you imagine you create this potential energy surface, and then the flux is moving, and then it looks for, it's exactly, imagine the meandering of a river through these hilly areas. So it looks for wherever it gets a path, it goes through that. And then, so this is done, there are involved calculations. So it is not just you calculate one barrier and you fix that, because it's a very dynamical thing. So the point is that as it moves through, what are the other, so barrier is, of course, I can fit most of that by data by just playing with the barrier, but that means basically putting all eggs in one basket. That will not be the right thing. We know the dissipative mechanism, which is basically coupling of the energy from this collective to non-collective degrees of freedom, also play an important role. So all these things have to be included in the analysis. And it's a very difficult problem actually to really say that exactly what is happening. But the first role is to get as much precise data that we can, and then try to also improve, calibrate the theory along with this against these advanced theories.
Thank you.
Yeah, Professor, I think Professor Panchpakashan has a question.
Yeah, please, Professor Panchpakashan.
Well, I really don't want to ask a question, but I was really very, very happy to learn that the IUAC, which is hardly 5 kilometers from my house, is deeply interested in the experiments that you're doing. I have frequent contact with Professor Pancholi, who goes there, who has been talking to me, but I never knew that fusion fission experiments are going on here. So next time you come, maybe we should get together there and discuss the whole thing. Thank you so much. Yeah.
That will be my absolute pleasure, sir. I look forward to our next meeting.
Sure. Yeah.
I just turn on my video to say hi to Indranil. Hi.
Hello, sir. How are you?
Okay.
Absolute pleasure. I just want to say that I showed Professor Mitra's this picture. This also adores my wall of my lab where I'm sitting right now, and it was such a pleasure that yesterday Ravi Rao was also showing some of the pictures from our meeting 15 years back. Any other question? Alok, is there any other question? I can.
Perhaps not. I don't see any raised hands, either via the cameras that are turned on or the icon.
What should I unshare?
Yeah, I guess so. Yeah, so we are now waiting for Professor Brajesh Chaudhary to join.
Okay. Yes.
I'm given to understand that he is joining. Yeah, there we go. So, Professor Brajesh Chaudhary, can you hear me and see me?
Yes, Alok, I can hear you and see you very well.
Lovely. So I would humbly request Professor Bhasin to kindly announce the next talk, please.
Are my slides visible?
Yes, indeed. But we'd request you to please go full screen.
Yes. File. View. Am I full screen now?
Absolutely. Excellent. So I once again request Professor Bhasin to please have the second talk started. Professor Bhasin, please.
Professor Hussain, you are muted. Please unmute.
He has been recently the head of the department, as we already know, and it is during his time that we had a meeting, condolence meeting of Professor Mitra during this for the last time, and he had really organized it very nicely, a very large meeting. I had really rarely seen this type of meeting which was there for some time. So thank you very much for Brajesh Chaudhary. He has been really going. He has been abroad for a number of years. Actually, he has spent many years in for Fermi Lab and also in Berkeley. I had the opportunity to have his hospitality at the Fermi Lab for a few weeks when I visited there. I therefore invite Brajesh Chaudhary to give the contributions of India's contributions to the CERN and LHC and CMS experiments. Thank you, Brajesh Chaudhary.
Good morning, and thank you for the introduction. It's my pleasure to talk at Professor N. Mitra Fest. I was not a student of Professor Mitra as many had been because I was not a student of Delhi University till MSc, but I came to know Professor N. Mitra when I was a PhD student with Professor R.K. Shupuri, and later when I joined here as a professor in 2004. And I met Professor Mitra several times. He passed away in 2022. I had the opportunity to hold the condolence meeting as well as a lecture in his honor. So this is, you have seen these pictures. I got it during the lectures that I had held in 2023. So this is my tribute to Professor N. Mitra. This reminds you of the inaugural memorial lecture that we had held on Professor N. Mitra's life and time, and it was given by Professor N. Panchapakeshan. So I come to LHC now, and what I'm showing here is an aerial view of CERN LHC, 27 kilometer of circumference. LHC is a proton-proton, proton-ion, and ion-ion collision collider. It has a circumference of 27 kilometers, and there are 4 experiments on it. They are called Atlas, CMS, Alice, and LHCb. And India collaborates on 2 of them, CMS, compact muon solenoid, and Alice, which is a heavy ion experiment. So CMS collaboration, and I would like to emphasize that some of these slides may not be very recent, maybe a year old or so. So take it like that. So CMS collaboration is about 260 institutions from 57 countries with about 6,000 members, but about 2,000 PhD physicists, of which 1,400 pays M&O, maintenance and operation costs. That means they are actively involved into it, about 1,100 PhD students and then engineers and others. India has only 31 PhD physicists, and the number of his students from India at any time varies between 60 to 75. So I'm not going to tell this august crowd about how our universe works, but I will just like to remind that our universe is 14 billion years old. And when we are working at 14 TeV, center of mass energy, we are going to the first 10 to minus 12, 10 to minus 13 second after the Big Bang, which is somewhere in the electroweak transition region, supersymmetry breaking region. And that's how we try to find about the, the quarks and the gluons and the forces that act between them and the vector bosons. So what is our universe made up of? We know that our universe is made up of 69% dark energy, 26% dark matter. So we know our universe is expanding. And that's what we call the negative pressure we call as dark energy. It's roughly 69 to 70%. But as all of you follow literature, I do also, and I'm not an expert on dark energy, there are various models of dark energy are coming that whether the rate of increase of dark energy is slowing down or what is happening. And there are better experts in the audience to tell about it. Dark matter, we know that there are matter which doesn't interact either with a strong interaction or electromagnetic interaction, but we see them through the gravitational pull, and they are the dark matter. So what I'm going to talk about is roughly 5% of the universe. And what we are interested in from the time of atom to the quarks and gluons. And I'm not going to go through this slide for this August audience. So we know about the fundamental particles and forces, 6 matter particles or 6 quarks, up, down, charm, strange, top, and beauty, and 6 leptons, electron, muon, and tau, and 3 neutrinos, nu e, nu mu, and nu tau. And the force particle for the electromagnetic force, photon, the strong force, the 8 gluons, for the weak force, W plus W minus, and Z. And now that the Higgs has been discovered, most of these particles, except for the neutrinos, interact with the Higgs field and they attain their masses. So the status of particle physics today. The status of particle physics is that the standard model is well understood very much. We do not know anything beyond this standard model, but then there are evidences of new physics which we are unable to explain very well. One is the accelerating universe, that is the dark energy. Second is the missing mask, that's the dark matter. Third, that we know that neutrino has masses and they mix. That means as they travel from one place to another at a certain distance, the mass eigenstate changes and the mix of mass eigenstate changes and they become, it is the flavor eigenstate, different flavor eigenstate appears. So we do understand that there are physics beyond the standard model. So some open questions in particle physics, which is interesting. And this came through the P5 report of the American High Energy Physics about 10 or more years ago, but it is still valid. What is the nature of dark energy, which constitutes 3/4 of the universe? What is dark matter and how one can find it? How did the universe begin? Then in the intensity sector, what are the masses and properties of neutrinos? What role did they play in the evolution of the universe? How are they connected to matter-antimatter asymmetry? Are elementary particles fundamental? And I have personally worked on quark substructure like Q star, B star, and others. How do these particles acquire mass? We know that Higgs boson, we have found the Higgs boson, and we know the answer that these fundamental particles, except for neutrino, interact with the Higgs field and they get their mass. But do we have only one Higgs boson or multiple Higgs boson? And we are still looking into it. What is the physics beyond this standard model? What are the new particles and forces? Do all forces of nature become one at some energy scale? And we know about the unification of the electroweak force. But does at some energy scale electroweak and a strong force also unite? We have no idea about it. Why there is matter-antimatter anomaly in the universe? What led to it? Obviously, when Big Bang happened, there was the matter-antimatter parity, as the basic physics will say. So what happens to all the antimatter? And as we know, with experiments in the space, we haven't been able to find much antimatter even in space. So what happened to the antimatter? And are there only 3 generations of particles? So these are all fundamental questions that none of the that experiments have answered till now. So energy frontier, this is the tunnel of the Large Hadron Collider. And what I'm showing here is basically the dipole magnet, one of the dipole magnets. So LHC, Large Hadron Collider at CERN, is the biggest and most powerful microscope in the history of mankind. It probes the shortest distance, somewhere between 10 to minus 18 to 10 to minus 19 meter. It has been in operation since 2010. Higgs boson was found in 2012. A Nobel Prize was given to the propounders of Higgs boson in 2013. And hopefully further discoveries may come. So I'm not going to go again through this slide for this crowd. As you see, one TeV proton, which was at Fermilab. That's why the accelerator at Fermilab was called Tevatron. It was able to resolve distance of 10 to minus 18 meter according to Louis Dubruy's equation. And 7 TeV proton is somewhere between 10 to minus 18 to 10 to minus 19 meters, the shortest distance yet seen in the universe. So LHC, as I said, is a proton-proton, proton-ion, and ion-ion collider, 27 kilometer in circumference, 100 meters underground for experiments. The accelerator ring has about 9,300 dipoles, quadrupoles, sextupoles, and octupoles. Dipoles are the magnet which bend the beam, moving almost with the velocity of light. Quadrupoles are the magnet which focuses the beam. Sextupoles and octupoles are the magnet which correct the various deformations when the beams are moving. The magnets are pre-cooled to liquid nitrogen, roughly 80 degree Kelvin. Okay, it's 77 degree Kelvin, using 10,000 tons of liquid nitrogen. And they are further cooled. The magnets are cooled to 1.9 degree using 60 tons of liquid helium. Construction time was roughly 10 years. There are 2 experiments, CMS and ALICE, on which about 20 institutions, each from India, are involved. So CERN accelerator, it is not one accelerator through which we go. It is 5 accelerators. First, it is a linear accelerator, number 1, which accelerates the proton up to 50 MeV. Then we get the booster, number 2, which accelerates the proton up to 1.4 GeV. Then number 3, proton synchrotron, or PS, which accelerates the proton to 25 GeV. And then the 4th is superproton synchrotron, number 4, which accelerates the proton to 450 GeV, which feeds into Large Hadron Collider, which is number 5, and it accelerates the proton to 7 TeV. So 2 protons, if I was saying electron, my apology, 2 protons of 7 TeV each collide head-on at different experiments. So on the left side, the picture is of a dipole. It is 1,230 of these 8.3 Tesla magnetic field dipole, which bend the beam around the ring, and they each weigh 28 kg. On the right, the picture is of the quadrupole, which I took personally, and you can see how the quadrupole looks. It is an old picture from 18 years ago. This is how, from the tunnel, the detector looks as I had taken the picture myself. Now, India's contributions to the Large Hadron Collider. I know people know the physics here, but everyone may not be familiar with all the contributions that India has made to the Large Hadron Collider over the last 30 years, and it is substantial. So India participated in LHC construction and commissioning, which was the cooperation agreement signed in 91, but India became more active, as you know, in a little later. And most of the contribution was in kind. Hardware contribution for construction of Large Hadron Collider, commissioning and recommissioning, and software development. Then India also participated in novel technology for accelerator project, NAT protocol, in which it made hardware combination, vacuum chambers, dipole magnets, and optics design and commissioning of the accelerator and control software. And then they are still working on LINAC 4, which has been finished for the superconducting proton LINAC. So what did India contribute? And I will read the top part of it. It gave liquid nitrogen tanks, 50,000 liter capacity, 2 of them. It gave superconducting corrector magnets, sextupole, decapoles, and octupoles, 1146 and 616. It gave 7,000 precision positioning jack on which the accelerator of Large Hadron Collider stands. It provided 5,500 quench heater power supplies. It provided racks 6,200, control electronics for circuit breaker of energy extraction system 70, local protection unit 1,400, superconducting dipole magnet measurement expert support 100 man-years. And then you can look through the slide. Here are the major contributions to the LHC. So superconducting corrector magnet on the left-hand side, it is from KECL Bangalore. Quench heater power supply from, again, ECIL Bangalore, 5,500 of them. Local protection unit from ECIL Hyderabad, again, 1,435. On the bottom left, precision magnet, about 7,000 made in Bangalore and Indore, on which the accelerator stands. And support for LHC hardware commissioning about 18 man-years. So main physics goals of the LHC experiments are test the standard model with very high precision, search for the origin of mass through the discovery of Higgs boson. Hopefully the same Higgs discovered, searching for other Higgs do if they exist. Search for dark matter candidates through the discovery of lighter supersymmetric particles, physics beyond the standard model, and understanding of the further 26% of the universe. Understand the nature of a space-time and unification of forces through search for extra dimensions and micro black holes. So we know that if extra dimensions exist, okay, we might be able to produce micro black holes which will have a certain signature in the detector. Also, there are extra dimensions model like Random Sundaram and other models which predict certain signature, but we haven't found them. Study matter-antimatter asymmetry to shed light on the origin of universe. Yes, LHCb has recently measured certain asymmetry, but that asymmetry is not good enough to explain the asymmetry in the universe. Understand the nature of Big Bang or primordial plasma to go back to the beginning of the universe. All these goals of the LHC are covered by the CMS experiment. And I would like to stress here that by now we have graduated about 120 PhD students. And the Indian groups has covered the full spectrum of physics analysis, from standard model physics, QCD, electroweak physics, top physics, Higgs physics, discovery of Higgs boson, TTH, Higgs pair production, to BSM physics like substructure of the physics or supersymmetry. We have explored all of them. So towards the high luminosity goal, we are in 1925. We are going to take run this year. Then there will be 3 years of shutdown. We will start again 2030, and then it will go for a long time. So India is involved in the detector upgrade, and now I'm going to come to that. So this is the compact muon solenoid detector. All of you must have seen. Inside is the tracker in the purple. In the green is the silicon tracker. Okay, it's made of silicon wafers. Then we have the lead tungstate crystal in the green color. Then in the blue color, we have the hadron calorimeter, which is made of scintillator and steel. Then we have the yellow and red part. The red part, before that, let me say there is this 3.8 Tesla magnet in white, which provides the magnetic field to all the charged particles that are coming out of the vertex. And then in the yellow and red, yellow are the muon system, and red is basically the steel substructure for the muon system, which also provides the magnetic field. I will skip this detector. So particle identification, as you know, that we look at the photon and electron in the electromagnetic calorimeter, pi plus, pi minus, neutrons and others into hadron calorimeter, and muon is the long particle that is curling out. So India's main contributions to the CMS detector. India started with outer hadron calorimeter, which is made up of scintillator and steel, and it measures jets and missing energy. Why it is so important? Because if you don't measure the jets and missing energy very well, you will not be able to measure the beyond a standard model physics very well. India also started with pre-Savar, which is on the left-hand side on the slide. What was pre-Savar? Pre-Savar was made of silicon wafers and lead plate. What it did, that it converted the pi zero into 2 photons, and the Savar from 2 photons will be very different from 1 photon. That was very helpful in disentangling pi zero, which is a background to the photon, and that thus the pi zero becomes a background for Higgs to gamma-gamma search. So these were in the initial phase. Then India put about a couple hundred muon RPC detectors. In the present phase of upgrade, India is already upgrading the muon measurement system with the gas electron multiplier for the high luminosity large hadron calorimeter. India is also making silicon outer tracker, which will be used for charged particle tracking, pile-up mitigation. India is also upgrading hadron calorimeter with electronics, which measures jets, missing energy, and lepton ID. And India is involved into EdgeCal with certain electronics. So this shows you silicon pre-Savar detector made by Delhi and BARC. We supplied about 2,000 modules. BEL Bangalore supplied it. Our students went there and they did the work there. I personally visited there, and it was about 50% of the total pre-Savar that was supplied to CERN. Outer hadron calorimeter was done by Punjab University and TIFR, and this shows you in the picture on the right-hand side, the red region where it covers the detector where the thickness was less. Then the resistive plate chambers, it has good position resolution with fast timing and signal collection, robust and highly efficient in triggering on muons in a busy environment. We provided 50 RPCs, high voltage, low voltage power supply. RPC was also developed by India-Alice collaboration. RPC can be used in medical imaging, tomography, and port security too. And you can see the pictures here of Delhi University and Punjab University. GEM detectors, you can see Delhi University and Punjab University. It is from the Delhi University picture. And on the right side, you can see the 3 GEM detectors with all of us. and 17 gem detectors has already been delivered for the run 2. And we have worked in close collaboration with Micropack for large area gem foil development for the next phase. And gem can also be used for X-ray imaging. This photo, I'm showing you that how gem detector can be used for X-ray imaging. On the right-hand side, you see some keys and metal objects are put there, and then X-ray is passed over them, and gem detector is on top and bottom of them, and you see their image. And what we do that after doing the analysis, here you see the mass thickness versus the hit density. So you can look at the objects while it passes through port security, that what kind of object, of what density object are going. And it is possible to use gem detector for neutron imaging. So this is the power of, this is the proof that has been published, but it has still to be industrialized. Various other detectors are being done. And here I can show you that the rate will be very high. On the top left, 140 collisions. In the middle, Sensor Qualification Center from the tracker for Delhi University. Aluminum carbon fiber stiffener produced at IIT Madras. Bottom left, hexaboard designed by Science Institute of Nuclear Physics, fabricated in industry. In between, indigenous fabrication of sensor and wire bonding, TIFR. And for the trigger system on the right, fabrication of high-speed FPGA board by TIFR. This has also given at grid computing at VECC and TIFR, and this is just a statistics for some period of time, but this has helped the computing system in the country. NKN technology came because of this, and as you can see, NKN technology is has connected the institutions in India. How much time I have? Hello? Hello?
I believe you have about a minute. Actually, okay. I would have probably considered that to be less than a minute, because you are hoping to also have a QA session.
Okay, fine. So few snapshots on physics. I am not going to go through the details, but these are the production and decay diagrams of the Higgs boson, gluon fusion, vector boson fusion for the production, and the Higgs boson with vector boson production and TTH production. So what I would like to emphasize, because Higgs boson is the most known physics from the LHC, Indian groups has contributed in all facets of Higgs discovery. Here, the two diagrams shows you Higgs discovery in gamma-gamma and Higgs discovery in ZZ is star going to 2 electron and 2 muon. Higgs boson was discovered. You have seen all these pictures. I'm not going to go through it. We have measured the Higgs mass to a very high precision. We have also measured the Higgs width, the Higgs coupling with various Higgs production and decay coupling with in the various modes, and you see that it agrees with the standard model, and it was published in Nature. We have looked at Higgs coupling to fermions and vector bosons, and you see that our latest result on the top in the left picture is the black cross is around 1, and then you can see that with the various particle which decays into the Higgs boson, which decays into various particles or couples to them, you see that they are coupling as a function of mass on the x-axis. Y-axis is the coupling fermion directly, and with the vector boson with the square root, it is on a straight line, so it fits very well. I'm not going to go into the future. Indian industries which partner towards CERN collaboration, it's a very long list. So Indian industry is heavily involved. This is the picture of Nataraj at CERN. Most of you have seen it. Professor Kakodkar, Dr. Kakodkar is in the background. That's the then CERN Director General and perhaps the Ambassador of India then. You can see there is this outside the CERN called globes. Here it's written Madhav Shankara Anant Sreni Bhaskaracharya Dutya Nakshatra Bas ki lambai का माप 365.258 दिन Brahmagupta Sunya and Rin Sankhya. So India's achievements are everywhere. Indians are doing well. This is my enlightenment in CERN itself. And very recently, 2025 Breakthrough Prize has been given in fundamental physics to Alice, Atlas, CMS, and LHCb, about 7,000 people or 13,000 people. There is a large number, but it tells you that the physics has been further recognized and India is contributing. So summary is India's contribution to CERN LSC program has been substantial. Indian physicists has contributed to every aspect of detector, software, maintenance, and operation to physics analysis from QCD, electroweak, top Higgs, BSM, dark matter, compositeness, SUSY to TTH and HH, Higgs coupling, self-coupling physics to heavy ion physics. We pay about 2.5% of MNO for CMS and are involved in about 8 to 10% of publications. We are doing very well. So thank you to all of you. Thank you to taxpayers of India, DAE, DST, and CERN for providing such rich opportunities. We are very thankful. I'm done. Thank you.
Professor Bhasin, perhaps if you deem it fit, we could have maybe one question or so. Professor Bhasin, can you hear me? Perhaps he might be otherwise engaged.
Haridas has a hand up.
Oh yeah, please go ahead, Professor Haridas.
Thank you for a wonderful talk. I was just curious that there's a lot of talk about the so-called Wakefield acceleration, which the proponents say will bring down the accelerator size by as much as 1,000. I was just wondering what your take on that topic is.
Okay, so first, I'm definitely not an expert on accelerator physics and Wakefield accelerator, but I have followed it to some extent. And Wakefield accelerator R&D was going on at Fermilab, and they have made some thing, where you can accelerate to a certain energy, but Wakefield accelerator on a larger scale where you can accelerate a particle like proton or electron to very high energy, let's say within hundreds of meters, is still, I will say, a dream.
Thank you.
I think with the permission of the chair, since we are about 5 minutes behind schedule, let us thank again Professor Bhasin for his chairing of the session, and Professor and the speakers of the session that he chaired, Professor Indraneel and Professor Brajesh Chaudhary. So we now would request Professor Bhale Rao to kindly chair the next two talk session. The first talk is going to be by Professor Ajoy Ghatak, and the other is going to be by Professor Tony William Thomas.
Yes. Is Professor Ajay Ghatak here?
Yes, I am here.
Okay. Professor Ghatak is going to talk on polarization of light, entanglement, and Wells inequality. Professor Ghatak.
If Professor Chaudhary can, I would like to share my screen. If you like to unshare your screen. Professor Chaudhary, Brajesh Chaudhary, if you would unshare your screen. Can you hear me?
Professor Ghatak, I don't know, perhaps he's, I don't know, if you start sharing, you'll get an option that you'd like to share.
It says that you cannot share screen while the other participant is sharing. So you have to unshare.
Achha, okay. Well, if you wish, I could do, because since we have your presentation, we could take care of your
All
files.
right. No, but I would like to do that, but let Brajesh Chaudhary unshare the screen. Then it becomes very easy.
Yeah, go ahead. Yeah, go ahead. Yeah, I think we're doing it for him. Yeah, it's
Okay.
done. It's done.
Can you see the slides? Can you see the slides?
Yes,
Yes.
yes.
Yes,
Okay.
you can see the
Okay.
slides.
Okay. Let me try to make it full screen. So we are little 5 minutes behind schedule. So I'm going to speak on polarization of light completely. I'm a little misfit here, but it is indeed a great pleasure and honor for me to speak on this very auspicious occasion. So my sincere thanks to Dr. Alok Mishra and Dr. Gargi Mitra for asking me to deliver a talk to this distinguished audience. And as I said earlier, I have never worked in particle physics, so my area of studies have been quite different. But even nevertheless, I find it interesting. So my deep respect to Professor Ashok Mitra, an outstanding physicist, and as you can see from the attire here, he was a remarkably simple human being. My interaction with him was during 1964 to 66, where I was for about a year and a quarter. I was a pool officer at Delhi University, and he was, of course, professor of physics. And I would often go to him for simple doubts, and he would be so nice, so warm, and it was a pleasure to interact with him.
Professor Ghatak, I apologize for interrupting you. You are still not full screen to us.
Oh, so then you share the screen. Oh, sorry.
Okay.
Sorry. Okay, you share the screen.
Okay, we'll do that. No problems. Just give me 15 seconds.
It says you cannot share screen while others are participating.
Oh, okay.
So I have not been allowed, so you share the screen.
Absolutely. Let's see. Here we go. So there are two versions, a PPT or a PDF. Which one would
PPT, PPT.
Okay. So share. Share. Go. Let's go full screen.
Yeah.
All right, we're there.
Okay. So, so it's my great pleasure to be present and a deep honor for this Professor Ashok Nath Memorial Meeting. Next slide. I wish I could do that. My sincere thanks to Dr. Alok Mishra and Dr. Gargi Mitra for asking me to deliver a talk to this very distinguished audience. And as I mentioned earlier, and my deep respect to Professor Ashok Nath Mitra, an outstanding physicist and a remarkably simple human being, as you can see from the dress that he's putting on here. I had briefly interacted with him. So during 1964 to 66, when I was a pool officer at Delhi University, and he was always very, very warm and very, very caring. My next slide, yeah. So the 2022 Nobel Prize in Physics was awarded to Alan Aspey, John Clauser, and Anton Zeilinger for experiments with entangled photons, establishing the violation of Bell inequalities and pioneering quantum information science. Next slide. So I will give a very, very elementary talk, very simple talk on experiments with entangled photons and establishing the violation of Bell inequalities. Next slide. So I thought I should mention that this is part of the National Quantum Mission. Our India is investing a large amount of money, DSTs, on National Quantum Mission, and understanding of the basic concepts that entanglement and Bell's inequality is very important. So the topic that I'm going to talk today is really quite important, although reasonably simple. Next slide. So understanding of experiments with entangled photons, establishing the violation of Bell inequalities are topics of great importance. Next slide. So the question, what is light, has intrigued mankind ever since he or she could see. Here I see a sadhu worshipping the light from the sun. Next slide. And as we all know, Isaac Newton, in his very famous book on optics, had put forward the corpuscular model of light and derived the Snell's law. Next slide. Then came Huygens, Christian Huygens, who around 1650 also put forward the wave theory of light and derived Snell's laws. Next slide. But it was around the middle of the next slide. The famous experiment, Thomas Young's experiment, 1801, which finally established that light is indeed a wave. He did the two-hole interference experiment, from which he could say that light plus light can produce darkness. Next slide. So this he did. So this is the simple interference experiment that proved that the light was a wave. But the question remained that how could it propagate through vacuum? Next slide. So Maxwell put forward the laws of electricity and magnetism in the form of four beautiful equations. He introduced the concept of displacement current and derived the wave equation. And therefore, he predicted the existence of electromagnetic waves. And he could calculate from the known values of electrical and magnetic constants that the velocity of electromagnetic waves in free space will be 311 million meters per second. Next slide. So the above value was very close to the value of speed of light measured by Fizeau in 1849, which was about 318 million meters per second. Next slide. And with faith in rationality of nature that these two numbers cannot be accidentally equal, Maxwell predicted the existence of electromagnetic waves and said that light itself is an electromagnetic wave. And he said this is the plane wave solutions of Maxwell's equations, as you all know. And what I have shown diagrammatically and through the equations is an X-polarized light in which the electric field oscillates in the X direction and the magnetic field in the Y direction. Next slide. So you can also have a right circularly polarized line in which the electric field at a particular point can rotate on the circumference of a circle, either in the clockwise direction to produce the right circularly polarized electromagnetic wave or the left circularly polarized electromagnetic. Next slide. And then came Einstein, as you all know, and 1905 was Einstein's year of miracles, in which, according to John Stachel, he wrote down 5 papers that changed the face of physics. Next slide. And in the second paper, in his year of miracles, Einstein wrote, light, radiation energy, consists of indivisible quanta of energy, E is equal to h nu. Next slide. And also the momentum of this light quantum that he introduced came to be later known as the photon, which has the momentum h nu by c. Next slide. So in 1926, Einstein's light quantum came to be known as the photon. Next slide. Now, if you have an unpolarized light like that coming from a sodium lamp, you put 2 thin sheets of polarides, and one polarizes, you have an X-polarized light, and then you have another polaride, which is whose pass axis is at an angle. So as we all know, the electric field is cos theta, Ex prime is Ex cos theta, and therefore the intensity varies like I0 cos square theta. So this is the famous law of Malus. Next slide. So you can do this experiment with 2 crossed polarides, 2 polarides oriented with one with respect to the other. In the first slide, first photograph, you have two parallel. So the most of the light will go through in 45. When they are inclined at 45 degrees, half the intensity will go through. If they are crossed polarides, 0 light will go through. Next slide. Now we consider a single photon source. So single photon source, you pass through a polaride and you get what is known as an X-polarized photon, which I denote by X, get X. And therefore, if it is passed through another polaride, then you have the probability of passing through becomes cos square theta. So no one can predict whether a particular photon will go through or not go through. You can only tell the probability of passing through, which is cos square theta. Next slide. Next slide. So you can have a 45-degree polarized beam, as you know, with a falling on an appropriately oriented calcite quarter wave plate and can produce a left circularly polarized ray. But if you have a 45-degree polarized photon and you make it incident to a calcite quarter wave plate, then it passes through the calcite quarter wave plate as an ordinary beam as well as an extraordinary beam. It is both with the S polarization and the P polarization, and it superposes with itself to produce a left circularly polarized photon. So you can have a left circularly or a right circularly polarized photon. Next slide. So the right circularly polarized photon has an intrinsic angular momentum of plus h cross. The left circularly photon has an intrinsic angular momentum of minus h cross. Next slide. And this was put forward by Satyendranath Bose in his famous manuscript that he had submitted to Einstein in 1924. But Einstein had deleted that portion. And so therefore, Satyendranath Bose never got the credit. Next slide. In a very recent paper in American Journal of Physics, I have tried to prove to the Western audience, I mean, the people in India know that he had actually put forward the concept of the angular momentum of the photon before the discovery of quantum mechanics in 1924. And I have tried to, in this small letter, I have tried to convince the Western scientists that it was Satyendranath Bose who had put forward the concept of this intrinsic angular momentum of the photon in 1924 itself. So last year we celebrated 100 years of the concept of the angular momentum of the photon. Next slide. So you have an X polarized photon can be written as a superposition of the right circularly polarized photon and the left circularly polarized photon. And if you make a measurement of the angular momentum of the intrinsic angular momentum of the X polarized photon, as you all know, there will be half probability of getting H cross and half probability of getting minus H cross. Next slide. So you have similarly a calcite crystal, and as you know, it exhibits double refraction. Next slide. So when an unpolarized light beam is incident normally on a calcite crystal, it usually splits up into two linearly polarized beams. Next slide. Next slide. So you have a sodium lamp and you pass through a polarized, appropriately oriented polarized, you have a 45-degree polarized beam, and you allow to fall on a calcite, appropriately oriented calcite crystal. So you have an X polarized, half the intensity goes through as an extraordinary wave as an X polarized beam, half the intensity goes through a Y polarized beam, and half the intensity is detected by D1, half the intensity is detected by D2. Next slide. If you have, no, previous slide, please. If you have a single photon source, and so, as I mentioned earlier, it is a superposition of the X polarization and the Y polarization, then it is in both the beams. It is in both the beams. And but if you make a detector, then, as we all know, it will collapse to either D1 or D2. Half probability of collapsing to D1 and half probability of but before you make the measurement, it is in both the beams, and both the beams can be quite a distance apart. Next slide. So you can, the device that I showed you is an XY device. No matter what the incident polarization may be, it will split into X polarization and Y polarization. You can orient the calcite crystal, and you can have an UV device that no matter what the incident polarization may be, the output will be U polarized or V polarized. And it can be sigma polarized or eta polarized or something like that, as long as they are perpendicular to the Z-axis. Next slide. So you can have three sets, I consider three sets of orientation of the device: XY device, UV device, and sigma eta device. Next slide. So I have a calcium atom which emits two photons in successive, quickly one after the other. And if one is X polarized, the theory tells us that the other will be, from angular momentum consideration, that the other will be Y polarized. So you pass through one photon through a XY device, and it collapses to being X polarized. Then the other photon, the other photon is entangled. It will collapse automatically to a Y polarized beam. Before the measurement, the polarization is at right angles, but I do not know the polarization. Next slide. So according to quantum theory, the polarization of the photon traveling to the left or to the right is not known before one of them is measured. I only know that they are at right angles to each other. Next slide. If the photon going to the left is passed through an XY device and it is found to be X polarized, then the photon going to the right collapses to a state in which this polarization state is Y polarized. So it collapses to being Y polarized. And these are the famous Alice and Bob experiments, and they can be millions of kilometers apart. Next slide. Similarly, next slide. Similarly, if Alice makes it pass through an UV device and it is found to be U polarized, then the polarization to the photon going to the right collapses to a state in which its polarization state is for sure V polarized. Next slide. Next slide. Whatever happened to one particle would thus immediately affect the other particle wherever in the universe it may be. Einstein, as you all know, called this spooky action at a distance. Next slide. So in 1935, EPR, Einstein, Podolsky, and Rosen wrote in a paper, physical review paper, that if quantum theory was correct, then two particles, if quantum theory was correct, then two particles which are millions of kilometers apart can be entangled in the sense that by determining a property of one of the particles, the property of the second particle can be instantaneously changed. Next slide. And special theory of relativity forbids that, and the transmission of any signal faster than the speed of light. And this came to be known as the famous EPR paradox. About 30 years later, experiments confirmed the predictions of quantum mechanics, namely Einstein's impossible proposition was in fact correct. Instantaneous changes in widely separated systems did occur. Next slide. So EPR argued that if without in any way disturbing a system, we can predict with certainty, that is with probability equal to unity, the value of a physical quantity, then the second particle must have possessed the measured property before the measurement was carried out. Next slide. So we assume the photon, therefore, we assume a simple hidden variable theory. Photon carries all the information. Thus, there must exist hidden variables so that we can assume values of all observables of a system. So if the left photon, I know that it is XU sigma. That is, if I pass through an XY device, it will be measured X polarized. If I pass through a UV device, it will be U polarized. If I pass through a sigma eta device, it will be sigma polarized. Then the right photon will be YV eta polarized. Next slide. Similarly, you can have left photon as YV sigma, and the right photon will be XU eta. Next slide. So since there are three orientations of the device, XY, UV, and sigma eta, there can be 8 possible combinations, nothing more. So, for example, in the fifth one, N5, let us suppose we detect N5 pairs characterized by YU sigma. If you pass through an XY device, it is Y polarized and so on. So I want, next slide, I want to calculate, say, P of XU. What does Px of U imply? That what is the probability of obtaining X polarization if you pass through an X polarization when you pass the left photon through an XY device, and U polarization when you pass the right side photon to a UV device. So P of XU corresponds to N3 and N4. And so therefore, next slide, therefore, P of XU will be N3 plus N4 divided by the total number of events that we occur. Let me do another example. So I next calculate P of X sigma. So P of X sigma is the probability that the left photon is X polarized. Left photon is passed through an XY device, and I measure it X polarized. And the right photon is passed through a sigma eta device, and I measure sigma polarized. So it corresponds only to N2 and N4 and no one else. And so therefore P of X sigma is N2 plus N4 by N. And next slide, I can have P of sigma U, similarly N3 plus N7 by 9. So if you add them up, you get so much. Next slide. And then P of XU is so much. So from which you get the because obviously we can see that the numerator of the first equation is larger than the numerator of the second equation. So P of XU is less than P of X sigma divided plus P of sigma U. What it means is this is the simple form of Bell's inequality, first put forward by John Bell in a remarkable 1964 paper. And he died at the age of 60 or 62. And otherwise, many people feel that he must have got the Nobel Prize. So let me now calculate what is P of XU according to simple quantum theory. So P of XU says that the left photon is passed through an XY device and you measure it to be X polarized. When you measure this to be X polarized, quantum theory tells us that the right photon is automatically Y polarized, collapses to a state which is Y polarized. So therefore, if it is Y polarized, as I had discussed in the experiment some time back, the probability that I will measure a U polarization will be given by the Malus's law. So half cos square pi by 2 plus theta, because that is the angle that the y-axis makes with the u-axis. So that is equal to half sine square theta. Next slide. So P of XU, according to quantum theory, is half sine square theta. Next slide. P of X sigma is half sine square phi, and P of sigma U is half sine square phi minus theta. So therefore, Bell's inequality, which assumes hidden variables, will imply, unfortunately it is not readable, sine square theta less than sine square phi plus sine square phi minus theta. Next slide. So thus, according to quantum theory, if validity of Bell's inequality will imply sine square theta less than sine square phi plus sine square phi minus theta, and if we assume theta is equal to 2 phi, then the above inequality means sine square 2 phi is less than equal to 2 sine square phi. And for phi is equal to pi by 6, we will have, therefore, sine square pi by 3 is so much. So this is an impossibility. And thus, quantum theory and Bell's inequality are not compatible, which implies that either quantum theory is right or theory based on hidden variables, but not both. So there are many experiments that have been done, and the most beautiful experiment is by Alan Aspect. Can I have the next slide? So according to which he writes, this is an apparatus for performing a Bell test, which was designed by Alan Aspect. And a source emits a pair of entangled photons of 2 different frequencies or 2 different colors. Their polarizations are analyzed by A and B, and the corresponding correlations and coincidence measurements are measured. Next slide. Alan Aspect writes, the linear polarization correlation of pairs of photons emitted in a radiative cascade of calcium has been measured. The new experimental scheme using 2-channel polarizers is a straightforward transposition of the EPR thought experiment. The present results, so they measure the P of XU and P of XV and things like that. They are in excellent agreement with the predictions of quantum mechanics and lead to the greatest violation of Bell's inequalities ever achieved. Next slide. So Bell's theorem represents, to quote Anton Zeilinger, as one of the most profound discoveries since Copernicus. Bell delivered, Anton Zeilinger got a part of the 2022 Nobel Prize. Bell delivered a death blow to the local realistic picture of the world. Many experiments have demonstrated that the predictions of quantum mechanics for entangled particles are fully correct, and the world is really as crazy as predicted by basic quantum mechanics. Next slide. You can do the same experiment using the famous Stern-Gerlach experiment. You see, as you all know, Stern-Gerlach experiment, you have a silver atom which has the magnetic moment of the electron, which has the angular momentum of the spin angular momentum of the electron, and therefore, by passing through an homogeneous magnetic field in the z direction, you make a measurement of the z component of the angular momentum of the electron, and it collapses to either z up state or the z down state. And next slide. And so if you prepare a Z up beam and pass through a Stern-Gerlach apparatus in the x direction, then there is a half probability of measuring the x up state and a half probability of measuring x down state. Next slide. So you can think of something like that, although these experiments are very difficult to perform, a singlet state, a positronium in the singlet state, electron-positron pair. And so therefore, it's a superposition of spin up and spin down and spin down and spin up. And if they are dissociated, then one will be spin up, the other will be spin down. The electron and the positron will be entangled. However, these experiments are extremely difficult to perform. It's much easier to do experiments with photons. Next slide. So the most fundamental theory now available is probabilistic in form and not deterministic, David Bohm. Next slide. So these are the most beautiful books on quantum mechanics. Dirac, Feynman, as you all know, quantum theory by David Bohm, and quantum mechanics by Rohan Tanuji. Next slide. And here is Dirac and Feynman. And David Bohm, as most of you will know, became a philosopher and became a disciple of J. Krishnamurti. And here in the third slide, you have Rohan Tanuji receiving the Nobel Prize. And on the right is Nicole and Dan Ostrowski, very good friends of mine, who translated the book on quantum mechanics. Next slide. What I have said today, all the slides are given in the 8th edition of my book on optics. Next slide. Thank you for your attention. Very simple talk, sorry.
Thank you, Professor Ghatak. Now, this talk is open for questions.
No questions, too elementary, no questions. Chalo, it's just 12, so we can go to the next session.
Okay. Okay, the next talk is by Professor Tony Williams from Adelaide. Professor Williams, Professor Thomas.
Hello.
Professor Thomas. Oh yeah, he's there.
How you doing?
Hi. Can you start now?
I hope so.
Yeah.
I'm trying to share my screen, but what happened? I can't see. Hang on. Let me just, I'm not sure what's going on. I see what's wrong. Okay.
Yes.
Okay, can you see that?
Yeah, we can see your screen.
Okay, let me just see if I can get full screen. Is that okay now?
Yeah.
Okay. So look, thank you very much for the opportunity to, I want to get rid of that too. Okay. Good. So thank you very much for the opportunity to talk on this occasion. It's a long time, it was a long time ago that I met Professor Mitra, but he made important impressions on me at the time. Just a few remarks on his work. How do I get rid of that? Just a couple of remarks I wanted to make about his work. It was remarkable how quickly he worked on both the Faddeev equations and the quark model within a year or two after the discovery of the Faddeev equations, and similarly after the suggestion of the existence of quarks. So I just noted a few of his publications that are worth mentioning. Already in 1965, he was talking about relativistic corrections to the Faddeev equations for the triton. He was also generalizing the three-body formalism to four bodies, something which, for practical application, took several decades beyond that. Quark model, he was working on it just a few years after Gell-Mann and Zweig. Calculating meson-baryon couplings in the quark model when many people didn't believe that quarks were real, but purely a mathematical artifice. In the 70s, joining together the ideas of low energy structure of the neutron and the deep inelastic structure functions. And touching on something earlier today with Stan Brodsky's talk, the light cone or null plane dynamics. These are remarkable papers and a great man. Let me come to the focus in my talk today. The relation to the work of Professor Mitra is through the Faddeev equations, which will be part of what I talk about. The main question I want to address is effective. Does anyone know how to get rid of this? Anyway, the question I want to address is effective field theory model independent? A great deal of modern nuclear theory uses effective field theory. The idea is that you construct a local nucleon-nucleon potential where the long distance chiral behavior is based on chiral field theory, chiral perturbation theory, and the short distance interaction is parametrized. But the point is that that interaction is local. The short distance parameters are adjusted to fit phase shifts over some range. And usually there's some power counting scheme to control the chiral theory. I remind you that power counting schemes are a human construct. They're not given by nature, and different practitioners are free to choose different power counting schemes. When you calculate the properties of a many-body system, either nuclear matter or finite nuclei, the two-body forces usually do not reproduce the data. And so one proceeds with the three-body problem in the same way. That is, the long-distance three-body forces are calculated using chiral effective field theory, and the short-distance three-body forces are adjusted in order to reproduce some selected set of data, either on finite nuclei or nuclear matter. And the claim is that this leads to model-independent predictions. I disagree with this. And the reason I disagree with it is I see no reason that the nucleon-nucleon interaction should be local. The nucleon is not point-like. It's a complicated eigenstate of QCD Hamiltonian. Its size is comparable to the distance between nucleons at saturation density. And there's no reason these complicated composite objects, which are not point-like, should interact through local forces. That is, phase shifts are not enough to constrain the theory. If changes in the two-body interaction, which don't change the phase shifts, lead to different predictions in nuclear matter and finite nuclei, then in order to reproduce those following the same prescription, you would need three-body forces, but those three-body forces would be different from the three-body forces you got with a local interaction. But the three-body forces, in terms of, say, Skirm theory or something else, are equivalent to a different density dependence in the interaction. And hence, the predictions for dense nuclear matter, or for finite nuclei for that matter, which involve different densities, will change. That is, they will not be model independent. So let me illustrate that with an old example, and I'm going back in time, but this is very relevant to what's being done today. So I'll give you an example from the three-body system. And this is work done with Irash Afnan a long time ago. The idea is to examine the effect of a unitary transformation which preserves phase shifts at all energies. We'll find that we constrain these unitary transformations by requiring that the one pion exchange tail of the nuclear force be unaffected and the charge symmetry not be violated. That is, that given A and N, which we can measure, that we should reproduce within reasonable error the scattering length for PP scattering. I'll illustrate this by showing you exact solutions for the three-body problem for the tritone binding energy and the ND scattering length. And for simplicity, the only part of the two-body potential which is transformed is the singlet S naught. For the three-body problem, it's the triplet S, triplet D, and singlet S naught interactions which are the most important. So how do we transform the Hamiltonian? We act on it with this is the strong nucleon-nucleon piece of the Hamiltonian. We act with a unitary operator to get a kinetic energy operator plus a different potential. The unitary operator is written this way, where HH is normalized to 1, and we take something that drives off exponentially and changes sign as 1 minus beta r. So there are two parameters in the unitary transformation. If the potential appearing in the Hamiltonian here is local, the transformed potential will have a velocity dependence and hence it's non-local. Now, if we look at transformations, beta's been fixed to 1 Fermi, wait, let me go back. Beta's been fixed to 1 inverse Fermi, and we vary alpha. You see the change in the short distance wave function, chi of k, as a function of that parameter in the exponential alpha. If alpha is very large, there's very little change from the unperturbed value. And as alpha gets smaller, the changes get bigger. Now, first of all, we don't want to change the long-range tail. So we remove these two, alpha equals 2 and alpha equals 2.4, because they modify the potential beyond 3 Fermis by an amount that's too great. So if we look at the effect on the tritone binding energy and the doublet scattering length for ND scattering, we see here the Phillips line. This is the original Hamiltonian. And this is the result as we decrease alpha. And so if increase to larger distances, the change in the transformed Hamiltonian, in interacting Hamiltonian. And we see as we do it, we move along the Phillips line. Alpha gets smaller, we move back along the Phillips line. And when we get to alpha 2.6, we start to deviate from the Phillips line. This is the region where we've changed the one pion exchange nature of the nucleon-nucleon potential. And so we exclude that region. Also, if we stick with alpha to be bigger than 2.8 or bigger, we preserve charge symmetry. That is, ANN and APP are consistent within 1%, which seems reasonable. However, all of the points along the line between 2.8 and alpha equals infinity are allowed. They all give exactly the same phase shifts to 0 to infinity. The only thing you're changing is the degree of non-locality in the two-body interaction. If, for example, you chose to reproduce the experimental value of the triton binding energy and the measured doublet scattering length by introducing a three-body force, the three-body force you would introduce with this interaction, with this interaction, with this one, with this one, with this one, those three-body forces would all be different. And so your predictions for nuclear matter or finite nuclei would be different. That is, they're not model independent. Now, what's this got to do with nuclear matter? Well, Fritz Coster and collaborators, including Ben Day at Argonne Lab a long time ago, carried out a similar study of the saturation curve for nuclear matter, in symmetric nuclear matter. And you see here the binding energy versus density. The correct saturation point's about here. But you see, as you make unitary transformations on the Hamiltonian, you can change that saturation point by an enormous amount. In every case, if you introduced a three-body force in order to reproduce the experimental value of the binding energy and saturation density, your three-body force would vary enormously. And hence your predictions for the properties, for example, of neutron stars would vary dramatically. That is, your predictions would not be model independent. Okay, so why am I concerned about this? Because I'm interested in a fundamental description of the atomic nucleus. And so let me just go through a few things which are of particular interest in this context. There are two views of nuclear structure. The EIC is concerned with mapping the quark and gluon structure of atomic nuclei. And implicit in that is that it's different from the quark and gluon structure of a free nucleon. On the other hand, nuclear physicists, many, believe that considering quarks is in contradiction to our modern understanding of nuclear physics, because the energies relevant for nuclear physics are only a few MeV. I believe that this second statement is wrong, and it's wrong for the following reason. We know that the intermediate range nucleon-nucleon force is a strong red scalar. In relativistic treatments, it's typically between 300 and 500 MeV. That's half the mass of the nucleon. It's not small. And so the argument that the mass scale in nuclear physics is different from the mass scale associated with quarks is quite wrong. It's true that the scalar attraction is cancelled by a large vector mean field, but that's a Lorentz vector. And its effect on a nucleon in nuclear matter is really just to shift its energy, whereas the large scalar field can change its internal structure. That's led us, starting with work by Pierre Guichon many years ago, it's led to the development of the quark-meson coupling model, where we start with a quark model for nucleons, and originally the MIT bag, later the NJL model. You introduce relativistic Lagrangian density with coupling of sigma omega and rho mesons to the non-strange quarks, and also the pion, but I'm talking about, I'm emphasizing here those that develop a mean field in nuclear matter. Initially, just 4 parameters, the coupling of these mesons to the quark, and the mass of the scalar field, which is not known. Fit those to nuclear matter properties and apply them to finite nuclei. Now, recently, we found we needed a 5th parameter in order to describe the giant monopole resonances. But implicit in this model is that the coupling of the sigma field to the quarks, to the confined quarks, means that you have to solve consistently for their internal structure. So we start with quarks. We go to nuclear matter. From that, we can go to neutron stars or dense matter. We can also get density-dependent effective forces and calculate the properties of finite nuclei. In nuclear matter, the effect of the change of the internal structure of the nucleon is that instead of the mass decreasing linearly with the mean scalar field, there is a tendency for the internal structure of the nucleon to rearrange in order to oppose that. And that's characterized by what we call the scalar polarizability, by analogy with the electric polarizability, if you applied an electric field to the nucleon. In the bag model, it's about 0.2 times the bag radius. This is equivalent to having repulsive three-body forces. For nucleons, 3 nucleons, a hyperon and 2 nucleons, 2 hyperons and a nucleon, all predicted by the model with no new parameter. It's entirely determined by this scalar polarizability. Now, one interesting thing when it comes to neutron stars is that the sigma field enhances the spin-dependent gluon exchange interaction between quarks, increases the sigma lambda mass splitting in medium, and hence we find no sigma hyperons in neutron stars at 0 temperature. I want to show you just a few results from finite nuclei. So this is across the periodic table, some 820 even nuclei. The color coding is the light green means that we're very close to the experimental binding energy. And you see that's true above the lighter nuclei, above N about 40 and Z about 20. The RMS radii typically agree within 0.1%. If we compare this, the most recent version of this model, QMC Pi3, the RMS deviation across those 820 even nuclei is 0.29%, which exceeds the accuracy of all other models except FRDM, which can't predict the charge radii and has more than 25 parameters. This approach has just 5 parameters. If we look at super heavy nuclei, QMC Pi3 are the red points, and the average deviation for super heavy nuclei, that is Z greater than 100, is 0.03%, which is outstanding compared with any other theory of super heavy nuclei. The super heavy nuclei were not fit. It was 70 nuclei across the periodic table, but much lower mass that we used to choose those 5 parameters. You can also calculate hypernuclei with no new parameters. You simply calculate the interaction of these fields with the non-strange quarks. It's the agreement with the 1s state in lead for lambda in lead is probably too good. More reasonable would be the 2 MeV agreement or 3 MeV with the others. This is a bit too good. But nevertheless, it gives a very realistic description of lambda hypernuclei, and it's also consistent with the few measurements of cascade hypernuclei. Let me come to neutron stars. Here we see the so-called model-independent equation of state developed by Anala et al., the green region being the preferred region. In this region, they used effective field theory, but effective field theory doesn't apply to neutron stars at low density because the surface of a neutron star is extremely complicated. It involves exotic nuclei, not neutrons and protons, exotic nuclei and pasta-like structures. And this model uses, in this model, we use a proper equation of state for the low density region in neutron star matter. But once we get above that low density region, and we're talking about neutrons, protons, and hyperons, we agree with the preferred region of Anala et al. And in particular, the kink here is associated with the production of hyperons in the core of the neutron star. Now, recently, neutron stars have become a hot topic because of new data coming from gravity wave experiments, LIGO and Virgo, and also from NICER, the satellite measurement of hotspots on neutron stars from which you can hope to deduce the radii and masses of the stars with reasonable errors. I show you the plot of mass in units of solar mass against radius for a neutron star, with the constraints from LIGO and Virgo and from NISA, with and without hyperons. And you see that at least at the moment, this same theory, but now relativistic, whereas the finite nucleus calculation was of necessity a non-relativistic reduction. But for neutron stars, you have to have a relativistic theory. And you see that for the moment, this theory is also consistent with the neutron star data and the tidal deformability coming from the quadrupole deformation of the neutron stars as they are about to merge with each other. One fascinating thing for someone not working in this field is that the core of a heavy neutron star, and in this case, this is the structure of, as a function of radius, it's the baryon content of the neutron star. So this is the fraction. And so this is 20% cascade minus, and that extends out to 5 kilometers. So for a heavy neutron star, this theory predicts that it consists of a huge amount of strange matter out to 5 kilometers, which is a pretty remarkable object. In summary, since my time is pretty much up, the complicated structure of the nucleon and hyperons suggests to me that the assumption of locality for two-body forces upon which effective field theory is built is too restrictive. If you allow non-locality, and in particular, you look at phase shift equivalent interactions, which don't perturb the long-range behavior of the interaction, you find large changes in the predictions for three-body systems and nuclear matter. As a consequence, the three-body forces, which in effective field theory are used to patch up disagreement with experiment, are not model independent. And as a consequence, the predictions for dense matter are not model independent. And I believe that there should be a lot of interest in approaches such as the one I described, quark meson coupling model, which are not built on chiral effective field theory, but actually describe data extremely well with many less parameters. Okay, I just wanted to thank to acknowledge a number of the people involved in the work I've described. Thank you.
Thank you, Professor Thomas, for a very comprehensive discussion. Now, any questions on this lecture? Questions, comments? Probably not.
Ah, well, that's a shame. Okay, I'll stop sharing. Thank you.
Yeah, let's thank both the speakers. And I hand over to Alok.
Right.
Indranil.
Thank you. Thanks a lot to the speakers, all the speakers, the pre-lunch session, day 2. I would like to once again remind us that today is Professor Ashok Mitra's birthday. So it's thanks again so much. There are a couple of announcements that I'd like to make. One is that if one were to go to the website of the meeting, one would see a revision in the schedule of day 2, which is today. So post-lunch, we're going to be having a pretty long session. So earlier it was comprising 4 talks, but now it's going to be comprising the 4+1. And a poor holographic joke that fits the bill. But anyways, so the speakers are going to be Yuta Kuntz, Daya Shankar Kulshresht, Patrick Dasgupta, who, by the way, is a bit under the weather. So we're going to be sharing a video prepared by him on his presentation. JD Anand, and the addendum is Naresh Dhadich. So he was scheduled to speak earlier today, but there were some issues, and so he'll be speaking at 5:30. So that will be the first part of the post-lunch session, and that will be on a separate Zoom link. And once again, all the updates and all the links, Zoom and YouTube are available on the website. And the second and the concluding portion of this meeting is the A.N. Mitra Memorial Lecture by Ed Witten. And that is going to be on a separate Zoom link, and that is scheduled at 6:30 p.m. Indian Standard Time, IST. So we have a rather long lunch break, an intervening lunch break, and we are supposed to reconvene in about 3 hours from now, a little less than that. So at 3:30 p.m. IST. And so thank you so much once again, and see you then. Bye-bye. So I'm ending the meeting for all. Thanks so much.
Bye-bye.
Okay.